Good afternoon, everybody. My name is Roya Dehkhaniri, and I'm working as a geophysicist in Equinor. The past few years, I've worked with CCS monitoring technologies, and I'm part of a committee of Europe SEG Net Zero workshop to arrange this workshop. Before we open the session for the second day of this workshop, I would like to say a few words about the purpose of this workshop, and then we open the session. As you all know, globally there is an accepted need to address the challenges of increasing greenhouse gas emissions that pose a global risk for climate change and environmental degradation. As part of a global initiative, the EU has adopted key targets to reach net zero emissions by 2050. Carbon capture and storage initiatives are one of the key activities in this road to support governmental targets and ensure transformation to a net zero emission-driven economy. We in Europe SEG Net Zero Group aim to strengthen knowledge sharing and increase awareness across the industry, and therefore we set up this two-day workshop. The day one was yesterday with a message from SEG President, followed by a keynote presentation by Philip Ringrose. In yesterday's session, we had focused on monitoring technologies for CCS. Today, we will have two sessions. Session one will focus on insights and risks for infrastructure for CO2 transport and storage. Personally, I'm very much excited for this session because this is not usually targeted in previous CCS workshops. The session two will address the business context of CCS, full supply chain activities and regulatory recommendations. Before we open the session for presentations, I would like to mention a few items as well. We have set up the agenda in a way that the Q&A session will be at the end of each session and not at the end of each presentation. Then please be prepared to raise your questions during Q&A. If you raise your hand, we will unmute your microphone, and we would like to have your video on, and we would like to have an interactive discussions during Q&A. However, if you don't have option to ask your questions orally, please write it in a Q&A question bar, and we will raise it during Q&A session, and we would like that presenters respond to questions orally that others benefit from these questions. With this, on behalf of the committee, I will open the day two of the session, this workshop, with presentation by Monika Sigrid from Equinor. The title of her presentation is Key Challenges from CO2 Transport to Storage. Monika, you are welcome to share your presentation, please.
I'm located in Norway, so of course this will be a little bit dependent when you all are located, but I wanted to say good afternoon and express in a way my pleasure of being here with you and having a chance to present to you the key challenges from CO2 transport to storage. And what I maybe would like to also add is that Roy already mentioned, I work for Equinor and I work in the material technology department, where we mostly focus on scaling and corrosion for, of course, oil and gas, but also we extend to CO2 transport and storage. I will check now, hopefully everything works. Let's see. Yes, very good. The plan of my presentation is designed like this, that I can in a way give you a little bit of taste of the value chain, and maybe many of you have already extended knowledge about it, but I will do it anyway. So you can have a little bit introduction to further what I will be talking about, and that is CO2 transport technology development actually in Equinor. Also dependencies and CO2 specifications, a little bit on the emitters, and not precisely due to companies, but a little bit more about their business and CO2 profiles that they emit. Balances between CO2 specification and the business, and as well chemical reactions that are very tightly related to material choice and experimental work that we do with different external companies, as well at the end conclusions. So I hope that you will enjoy and that later we will have a great Q&A session. So if I now go to the value chain and you can see the figure. So you can see in the figure the area that is marked in a dotted line. And this area is representing the borders to what we will refer to as a transport value chain. And then after, I hope that you see my mouse. And of course, after the transport, we have also the storage area. So this means that in a way, the capture process is not included in our definition of transport value chain. So that is something to be aware of. At the same time, we are very aware that the capture will affect the composition of the CO2 specification, and therefore also, of course, the transport and storage. There is possibility of different concepts, and these are just a couple examples here, so I don't go through very detailed about multiple other concepts that we have in Equinor, but the one that in a way we refer to the most is onshore facilities that are actually located in Norway. We have also trunk line from Europe to Norway, and we can have different solutions for offshore offloading from ships. So maybe I can just say one sentence referring to trunk line from Europe. And I know that many of you know that the trunk line will be operated by Equinor, and it is around 1,000 kilometers where the CO2 will be transported from Europe to Norway as a final location. We can also discuss it more if you will have questions later to what I can share. But in a way, that's one of the biggest and more complicated solutions that we have. If I go further, let's see. What you see now at the screen is the different overview of different regions or areas that Equinor is working in. And in order to make all happen when it comes to CO2 technology, we of course have to have development that plays a significant role. And I would just like to stress that although I will be focusing on transport, it is also important to know, of course, that everything affects everything. So also storage is affected by transport. So Equinor puts a lot of importance on the CO2 specifications and the considerations in this area or to materials. And what I mean here is, of course, the materials selection for the pipelines, but also for the ships. And here we're touching up on corrosion, on sulfide stress cracking, on hydrogen embrittlement, and so on and so on. And this is connected also to chemical reactions and thermodynamics and hydrates and so on and so on and so on. So that's one of the areas that we in a way divide our research in. We have also area into CO2 engineering tools, and there are different activities from cost evaluations, flow assurance evaluations, of course, process simulations, and safety, thermodynamics again happens also. And then we have the last area that is CO2 facilities, and it's touching up on already on the storage, but it's not purely storage that I'm mentioning, of course. And that is ship transport and offloading structures and controls and what pipelines do we choose and sizes and metering and so on. So these are the three main areas for transport for CO2 that we work on. Let's see, going to the next one. And I wanted to keep this presentation in a little bit more style where I can, in a way, ask questions also to you and to maybe provoke certain questions later. So that's why I put this slide. It's a very black and white slide, but the idea is to highlight very clearly that, okay, we want to transport CO2, and in many years back, it was thought, okay, it's very easy. We just transport CO2, it's fairly pure. There is small impurities that can be included, but they are so tiny that nothing can happen, right? So the attitude years back was, what do we transport? Oh, just CO2, it's one phase and everything, it will be very easy. But of course, once everyone start to research and to understand, to plan, to design, it's often like this that the questions come up, that more knowledge we don't know, it's then being built up, and therefore challenges in estimating vapor return, understanding the flow assurance and what it means if we suddenly have two-phase flow, or how to avoid it, or any other challenges for flow assurance. Of course, thermodynamics for the different parts of the impurities, as well as evaluations of, for example, shall we have TEG, MEG in the pipelines? Should we not have it? Everything there is very important. Also, material choice and qualification, and that's connected to chemical reactions. How big the pipelines can be, what can we allow, what's practical, and to which extent actually also conditioning and liquefaction will affect the pricing for emitters, as well as what is the result of choosing certain conditioning technology, what is the result for the impurities. So it's not so easy as we might have thought many years ago. And many of you might know the specification that is published. And what I say published means this is not the last version. There is always updates, but this is what is published. This is a specification for Northern Lights joint venture. And we have different concentrations of impurities that are listed in between water, oxygen, sulfide oxides, nitric oxide, carbon monoxide, different amines, ammonia, and so on and so on. And this is, in a way, I could say, shortened list. We are aware that there might be more impurities that can come into the picture. And of course, what we are doing is working further to understand the implication of the impurities. I think I wanted also to mention that if we are talking about the transport, we have to think, for today, of course, there are different options and sensitivities, but generally when we talk about ship transport, we can refer to the temperatures around -25 Celsius and around 20 bars. Of course, we can deviate and from these temperatures to a certain degree, and depending on the demands of the different project, this might change, but that's a general. And for the pipeline transport, what we are referring to is 100 bar pressure and around 25 degrees Celsius. And again, of course, this is a little bit different. We can also say that 4 degrees is relevant if you have a pipeline at the bottom of the seabed, and so on. But that's what we refer to when we are where we are saying pipeline transport or ship transport per today. And then I wanted to challenge a little bit. So I have shown in the previous slide the joint venture, Northern Lights joint venture specifications. And these, of course, are referred to by many as strict. And then, in a way, one can see maybe certain conflict that can arise between emitters and, for example, companies that will receive and store the CO2. And the conflict is that, of course, different emitters will produce different impurities in the different degree. And the portfolio, if you can call it like this, the portfolio of different impurities, it's very, very long, very wide in a range, in specifications. And this poses a little bit a challenge to which you can say how is it for different emitters? What will they produce? How should it be handled? Is the specification that we are designing correct and good for both emitters and companies that will handle the CO2? So it's a balance. As you can see, for example, biomass fermentation can have alcohols, aldehydes, methane, H2S, and so on. And as we go a little bit farther, if we have, for example, natural gas processing, and as long as it's amine-based, we will also have nitrogen and might be a lot of oxygen and so on. So the profile of the emitters is very different. And now, in a way, the question is, where is the balance between what the cost of the purification and different methods are, and to all other things that the company that has to handle CO2 to store it has to incur. And in a way, the purification costs can be high, but also, of course, the transport and storage can be quite high. So we can have, as I mentioned already, unexpected to face situations and slugging and cavitations, and because of that, less effective flow. And we can have metering errors because of different upsets. We can have chemical reactions that will then cause corrosion, and then we can have precipitation of different species that will then affect also flow and will affect the corrosion. And we can have toxicity that is high and hazardous leakage to the nature. And we, of course, can have hydrate challenges and ice and sulfur and carbonates and so on and so on and so on. So I think that the very, very big challenge in the value chain, as I see it per today, is how to set the specifications that everyone will be happy. And that is a very, very big question mark today. But since I mentioned that I will go into key challenges, I would like to touch up on chemical reactions. And chemical reactions is that you can see actually on the screen. These are the reactions that were discovered in a work that we are doing with our external partner, that is IFE, that have a very good rig that I will show in the next slide. And these chemical reactions are very important because, of course, as you can see on the screen, in point 3 and point 4, you can create acids. In point 5, you can create a solid sulfur that, if there is presence of water, of course, it can also be corrosive, the same as sulfuric acid and nitric acid. And this is a challenge because many pipelines, for example, are not planned to be pigged, or maybe we have to plan it to be pigged. And if we have any suspicion of possible corrosion, we have to quantify it. And how do we do that, right? So that's why it's a very important work that IFE is doing together with Equinor and other companies that are in the GIP to try to quantify the result of acids that precipitate in a pipeline or ship. What does it really mean for the chain? What does it mean for material choice? What does it mean for the flow? How will the acids in a way perform in the flow? Will they be in a bulk phase as small droplets? Will they be as a film in the pipeline? Will that affect in any way thermodynamics of other components? So there is a lot of questions. And on the picture, in the picture, you can see that the created acids were in the form of liquid. So, and then we also had different solid components, like sulfur or like carbamides. So let me go further. And I said I will share with you how the IFE rig looks like for testing chemical reactions. And here I wanted to also mention that there is also work that Equinor is doing with DNV. I don't have the slides on the rigs, but I wanted to mention it because that's also a very important work where we study sulfur stress corrosion cracking, and also how that relates to general corrosion. But here you can see in a way the autoclave like chamber where IFE is conducting on all the experiments. And you can see, I hope you see it, there are small coupons that are hung in a bulk phase of dense CO2. And then there are small pipelines that come into the autoclave that inject the correct impurities amounts, concentrations. There are different, at the bottom, you see pictures with cylinders, and these cylinders have different stock solutions that are injected to the reaction chamber, that is the autoclave. And then we observe the reaction and we monitor them with the ProCIAS instrument that you can also see just example of what we get in the right bottom corner. So we just at the on the basis of what we see from the analyzer, IFE and the members discuss in a way what we believe has happened, and if we created any different components that can then be tested and evaluated if they have influence on the corrosion and on materials. And I also wanted to mention last partner that we also work with is extensive GIP with wood, where we actually try to address with other companies all these different aspects of CO2 and their specifications to come to the guideline development. And here you can see that it covers most of the challenges and areas that I have mentioned, from thermodynamic to CO2 compression and pumping, to capture and conditioning, to metering and geological storage, and of course it should also include economics. So we hope that at the end of this GIP, together with other companies, we can come to certain conclusions to how to, in a way, choose the correct specifications for different purposes. So I guess my presentation is not very detailed. It's a little bit general, but of course, if you have any questions later, you can also contact me, but or have questions later today, you're very welcome. But I would like to just conclude with three main important conclusions. And I believe that it is that specifications are actually quite sensitive depending on the emitters and flow, pressure, temperatures, thermodynamics, vapor nature, and monitoring. Also, it's very important to notice that specifications for CO2 transport are actually considered quite stringent at the moment. But maybe with time, we can evolve more and understand more the issues and maybe propose different solutions that can, in a way, fit better the business. And the challenges lies in finding actually per today the golden middle that will be satisfying for clients as well as the suppliers. So in that case, Equinor, while also development projects and project acquisition is ongoing at the same time. So thank you very much. And I would like to just take this chance to say also thank you to all my colleagues at Equinor that have contributed to making this presentation. Thank you very much.
Thank you, Monica. We're going to move on to the next speaker, and the questions are going to be taken at the panel session. So our next speaker is Gareth Hines from National Physical Laboratory. He's going to talk about composition of CO2 and impact on infrastructure integrity. Gareth.
Thank you, Adriana. Good afternoon, everyone. First of all, I'd like to thank the organizers for the opportunity to present. I think they've done a great job in lining up this session. Monica's presentation was the perfect introduction to mine, which is a little bit more technical. I do apologize in advance for any technical detail that might be a little bit too much. I've tried to keep it as high level as I can. And then Marcel's talk nicely follows on from my focus on corrosion testing to how to monitor corrosion in the field. So first of all, a quick word on who I am. I'm based at the National Physical Laboratory in London, where we are the UK's national standards laboratory, and I work in the electrochemistry group. Our main research in that area is on test methods, measurement techniques, and standards, mainly for corrosion and material degradation, but in a wide range of applications, not just oil and gas, carbon capture, but nuclear waste storage, offshore wind, batteries, fuel cells, and electrolyzers. I'm also quite heavily involved in corrosion societies. I'm currently president of the World Corrosion Organization, vice president of the European Federation of Corrosion, and a past president of the UK Institute of Corrosion. So I think what you can learn from that is that I'm not very good at saying no to things. And indeed, I'm here today. So a quick word on NPL, for those who haven't heard of it. We are the UK's national standards laboratory. We're over 100 years old. There are over 1,000 scientists and engineers based in Teddington in southwest London and at some regional sites scattered throughout the UK. And we are owned by the UK government. Before I get into the meat of the talk, I'd like to acknowledge my co-authors, Shravan Carey, Singi Zhu, and Alan Turnbull from NPL, and funding from the UK National Measurement System. So I think, as I said, Monica's given a great introduction to CO2 transport. I'm specifically going to talk about materials selection today, and in particular, how we go about assessing the corrosion rate of materials in dense phase CO2. So there are two ways of transporting CO2, both pipeline and ship, as Monica mentioned. I'm focusing mainly on pipeline transport, which, as she mentioned, is typically around 100 bar and either side of room temperature. So for those of you that may not have much of a background in corrosion, and I suspect that's the majority of you, I'm just going to say a little bit about corrosion. There's been a lot of research in corrosion going back more than 100 years, and particularly in the North Sea area, countries like Norway, like the Netherlands, like the UK, who have been taking oil and gas out of the North Sea since the 1950s. There's a lot of work done on what we call conventional CO2 corrosion. And CO2 is acidic. Those of you that do chemistry will know that it dissolves in water and dissociates to form carbonic acid. And the CO2 that's present in oil and gas reservoirs can then acidify the aqueous phase that's transported in the pipeline. And this can lead to several different corrosion mechanisms. So the one that we're mainly focused on in dense phase CO2 is internal corrosion. You can prevent external corrosion of the pipeline using coatings and cathodic protection. But internal corrosion is more of a challenge because you can't really control what's in the fluid to the same degree. And there's a lot of learning to be gained from conventional CO2 corrosion, but in dense phase CO2, there are a lot of differences as well. And it's those differences that are the challenge and that are requiring us to do more research to understand the corrosion mechanisms and therefore be able to mitigate them. And as Monica mentioned, a lot of the research going forward is about reducing the level of conservatism that is present because of lack of information. So the more understanding and knowledge that we gain about the system, the less conservatism that we have to build in, which comes with additional cost. So corrosion is an electrochemical reaction. It consists of two separate redox reactions, an anodic reaction, which is dissolution of the metal, in this case, iron going to iron 2+, and a parallel coupled cathodic reaction, which in CO2 corrosion is usually reduction of protons to form hydrogen gas. And the electrons that are transferred at the anode then travel to the cathode through the material. And so you have a coupled redox reaction with an anode reaction and a cathode reaction leading to dissolution of the metal. And this can lead to perforation of the pipeline. If the corrosion is localized, this can happen quite quickly and be quite catastrophic, or you can just get general wall thinning of the pipeline over time, in which case people tend to build in what we call a corrosion allowance to make the pipeline wall thickness thick enough for the pipeline to tolerate this gradual wall filling. Now, the mechanism of corrosion in dense phase CO2 is slightly different to that in conventional oil and gas pipelines. Here we have a dense phase with a small number of impurities. Again, Monica gave a nice introduction to where these impurities come from. These impurities tend to dissolve in any condensed water and form acidic solution that then leads to these electrochemical reactions. And you can get then what we call pitting of the surface. These pits then join up and eventually they can lead to cracks in the presence of stress, or they can perforate through the pipeline wall over time. And I guess the main take-home message here is that condensation of water is the key issue here. If you have completely pure carbon dioxide in the pipeline, no corrosion is possible. So this only happens in the presence of impurities, and the most important impurity is water. So how do we test for this in the laboratory? Now, we recently carried out a literature review of corrosion rate measurements over the past 20 years or so. There have been several research groups across the world putting a lot of effort into designing test methodologies for measurement of corrosion rate in dense phase CO2 with different impurities. Monica showed you an example of the one at the Institute for Energy in Norway, and they would be considered the world leaders in the development of these test methodologies. So here's an example of one here. It's an autoclave, in other words, a pressurized vessel where you can pump in CO2 and different impurities to control the environment that the specimens are exposed to. These are metal specimens, coupons of the pipeline material, usually cut from a tubular pipeline itself, so that the metallurgy of the specimens matches that you see in the real pipeline in service. Then some liquid water is placed at the bottom of the autoclave. Its mass has to be carefully controlled so that the composition matches, again, the worst case scenario typically that you're envisaging during service. And then the specimens are typically mounted into the autoclave. You purge the autoclave. It's really important to remove all of the oxygen because oxygen is an alternative cathodic reactant in the corrosion reaction. You want to minimize that level because there is very little oxygen in the stream in service. Then the gaseous impurities are injected in a controlled manner. The autoclave is then raised to the pressure and temperature of the test. Then you maintain those conditions for the duration of the test, which can be anything from a few hours to several days or weeks. And then finally, the autoclave is depressurized. The specimens are removed carefully, they're cleaned. And then the mass of the specimens is carefully recorded. And then by comparing them with the initial mass, you can determine the amount of mass loss due to corrosion that has occurred during the test. So that's a typical corrosion test. Some of the details of the methodology vary, but most of these things that we've listed here are common to all methodologies. Now, the problem arises when you look at the literature, and this was quite surprising to us. We did a very systematic review of published corrosion rate data in the literature. And really, the bottom line is that there is no consensus whatsoever. There is a real reproducibility problem in the measured corrosion rates that are reported by different laboratories, and even between the same laboratories in some cases. So even under the simplest conditions where the only impurity in the CO2 is water, the measured corrosion rates can differ by up to an order of magnitude, a factor of 10. So, you know, this makes it really difficult to compare results from different laboratories or to have any confidence in the reported data that are published in the literature. So what types of things influence the corrosion rate in a pipeline? Well, there are two types of factors that are associated with the fluid itself. So the level of impurities, the pressure, the temperature, and the flow rate, and factors that are associated with the material of the pipeline itself. So the grade of material that's used, whether it's stainless or carbon steel, whether there are welds there, the surface roughness of the material, and any stress, particularly residual stress from the fabrication of the material. But I mentioned water being the most important thing, and it really is. If you can keep water, and that is liquid water, if you can keep liquid water out of the pipeline, the chances are you won't really have any corrosion problems. And of course, that comes at a cost. If there's a lot of water in your inlet stream coming from different emitters, then it's going to cost you money to clean up that stream. And so it's a trade-off between protecting the integrity of your pipeline over its design life by removing the water and the cost of removing that water. So as Monica mentioned, it's about finding that sweet spot between cost and performance. And we do that by gathering information and learning more about the mechanisms of condensation, the fluid transport, the thermodynamics of the fluid, and the impact of the impurities when they do condense on the corrosion rate of the material. So typical operating pressure, this is a plot of the solubility of water in dense phase CO2 and in gas phase CO2 on the left-hand side. You can see the transition in solubility when the CO2 changes from the gas phase on the left to the liquid phase on the right. And typically the CO2 is transported in the liquid phase. So here at 100 bar and 25 degrees Celsius, for example, the solubility is just over 3,000 parts per million. What happens when the pressure drops? And this can happen maybe due to an upset in conditions in the pipeline or at a particular component of the pipeline where there is a pressure drop. The solubility can dramatically drop at any of these temperatures. And particularly at lower temperatures, the solubility in the gas phase drops down to quite low values. And this means that allowing for this, pipeline operators often have to set quite low levels for the water specification in the CO2 composition. And many operators set limits as low as 50 ppm to make sure that liquid water doesn't appear in the pipeline. Now, obviously, cleaning the CO2 up to that level brings additional cost. So anything that we can do to understand and mitigate the corrosion will really help with this cost. So how do we test in the lab? There are several different types of autoclave setup that are used. So from simple static autoclaves where the specimens are just suspended in the autoclave, the fluid isn't moving other than being stirred to ensure that the environment around the specimens is constant. Then I note that Monica's already showed this nice setup from IFE where they have a camera with a transparent window in the autoclave. And this has been really useful for studying the phase behavior of the water, what you can see using the camera and the transparent window, where we get condensation of the water and when, as a function of the conditions in the autoclave. Another type is the flow loop. These are typically the most expensive type of autoclave setup and the most challenging to achieve conditions similar to what you see in the pipeline. So here we typically have thinner, longer autoclaves with high pressure pumps to pump the fluid around. And that simulates most closely the conditions that you might see in a pipeline. And then there are kind of intermediate setups where we have a rocking or a rotating autoclave. Again, this one is at IFE in Norway. And these can simulate flow by every time the autoclave is rocked. The specimens are on a kind of sliding mechanism. So gravity then shoots them up and down and simulates the flow past the specimen. However, all of these setups have their pros and cons, and we need to use a combination of all of them to fully understand how to measure corrosion rate most accurately and make it as representative as possible of service conditions. So the issues that have been identified with common test methodologies are as follows. There's a lack of control of impurity concentration. These impurities can react together. They can be consumed in corrosion reactions, and they can be lost through evaporation, for example. So it's very important that throughout the whole duration of the test, the impurity concentration is controlled properly. Secondly, we need to remove any influence of oxygen by deaerating fully the autoclave. A third problem is that when we pressurize the autoclave, if we have liquid CO2 at the bottom of the autoclave before the test starts, the force of the dense phase CO2 entering into the autoclave can actually impact on the liquid water and splash it all over the test specimens. And this is something that is non-representative of fluid in the pipeline and leads to higher measured corrosion rates than reality. Similarly, when we're cooling down the autoclave and depressurizing it at the end, we can get, if we're not careful and we don't do this properly, we can get water condensing on the specimens and adding additional corrosion that isn't realistic to the apparent corrosion rate. And then finally, if the test is not long enough, we can fail to make an accurate measurement of corrosion rate. So all of these things add up to what we've seen in our literature review, that we have a very big range of corrosion rate being measured under what are nominally identical test conditions. And this is a problem for making decisions and for consensus among the research community. So I'm just going to mention briefly some of these problems and how they could be addressed. So with control of impurities, it's really important to measure the impurity levels. So this is typically done using spectroscopic or analytical techniques on the outlet of the autoclave to make sure that impurity levels aren't being depleted during the test. From the accidental wetting point of view, these are some nice pictures from IFE that show the splashing of water on the test specimens. And what you can do about it is to separate physically the specimens from the liquid water so that any splashing that occurs doesn't actually impact on the specimens. But not every lab does this. In terms of test duration, there's actually an issue here for people to be aware of, that the incubation time for dissolution of the liquid water in dense phase CO2 is actually quite lengthy. So it can take up to a day or sometimes even 2 days, depending on the conditions, for all of the liquid to dissolve in the CO2. And that means that if you don't wait long enough for that to happen, you're not carrying out the test under the conditions that you expect. So to summarize, we do have a reproducibility problem at the moment in the published open literature on corrosion rate of pipeline steels. And this is because it's very difficult to control the conditions in these types of tests. We need a standard test method, and in my organization, NPL, we work on standard test methods. We have a long history of developing standards that can be rolled out to test houses that can generate robust, confident data that allow operators to make decisions, for example, on their CO2 specification and on their material selection. So we've just kicked off a research program, and in fact, we are also involved in the joint industry project that Monica mentioned on the materials corrosion work package, where we're feeding in information on the development of standard test methods and how to control test parameters and generate more reliable results in testing. So finally, just to step back a bit and ask the question, what are the implications of all of this on the CO2 transport? Well, firstly, at the moment, because of this lack of consensus on corrosion rate and mechanisms and how phase behavior affects corrosion rate in particular, operators need a high degree of over-conservatism in material selection. So this means selecting a more expensive material in situations where you don't have enough information on the corrosion rate and there is a relative lack of service experience. So projects that are being delivered now are probably overcosted because of this over-conservatism. So this will have to change in the future with more research and with more understanding of these different mechanisms. The second thing, and Monica's already touched on this, is that CO2 specifications are tightening all the time. They're likely not sufficiently conservative, particularly because of acid dropout. And this is where the different SOx and NOx and H2S impurities in particular can react together and combine with the water to form very acidic aqueous phases, essentially nitric and sulfuric acid that will eat through the pipeline material. And thresholds for acid dropout are still based on very limited available data, and particularly data at low temperature. So we need to gather more information and more understanding on acid dropout in particular to be able to set more reliable and cost-effective CO2 specifications. So I will draw to a close there. I'd like to thank you for listening, and I'm very happy to answer any questions. I'd also direct anyone who's interested in more information on test methodologies for pipeline steel and dense phase CO2 to our recent review paper, which was published in Corrosion Science. And thank you very much for your attention.
Thank you, Gareth. So we're going to move to our last speaker before the panel discussion. The next speaker is Marcel Grubert from Halliburton. Marcel will speak about pipeline integrity monitoring with DAS. Marcel.
So my name is Marcel Grubert. I'm with Halliburton since last year. I am the principal technical advisor for fiber optics. Mainly I'm working in the upstream, which means now it's getting the oil and gas out of the ground. But I got some previous experience with OptaSense, which is distributed acoustic sensing, fiber optic measurement and acquisition company. So now they are heavily involved in oil and gas, but also in pipeline monitoring, infrastructure monitoring for bridges and so on. And before that, I was 10 years with ExxonMobil as one of the production enhancement specialists. So I'm going to talk about pipeline integrity monitoring using distributed acoustic sensing. And the first question is now, what is fiber optic sensing? So in fiber optic sensing, you're going to have a fiber optic cable, very similar to now what people run for their now internet fiber optic cable now that connects all the houses and cities and so on. That fiber optic cable has, when they manufacture it, they're going to have some inconsistencies in it. So I'm taking that fiber optic cable, I'm putting an interrogator on one end, which is now just a box that produces a coherent laser light. And I'm shooting that light through that fiber. And because of those inconsistencies in the fiber, parts of that light is going to get back reflected where it was coming from. So that pulse is going to travel down the fiber, and as I said, as ESA shows inconsistencies, it's going to get back reflected to the surface. I have to wait until the pulse runs all the way to the end, and then it for the rest of the light to then come back to the interrogator. And the interrogator not only creates the laser light, but after it sends the pulse, it starts looking for the returning light signal and then makes a map out of it. So fiber optic cable is very, very sensitive to any strain impingement on the fiber itself. So anything that can influence it and slightly bend it out of shape, which could be now any reservoir movement, any rock movement, any acoustics impingement on that, any pressure impingement on it, any temperature changes on it. So with that, we have a very, very sensitive measurement methodology that can now give us an idea what's happening along the fiber, every single meter along this, as I said, very, very long fiber. So that fiber optic cable you see down there is an example. You got that fiber optic core, and then we have several claddings to not prevent any reflection or light reflection out of the fiber, as well as now to protect against environmental influences, to strengthen the fiber to make sure it's not going to break, and then we have an outer jacket. And in general, you have multiple fibers within now those assemblies. So we got now normally 2, 3, or even 4 of those. There are 2 different kinds of modes on those fiber. We call this multi-mode and single mode, and that's based on the thickness of the core. Now there's a 50 micrometer thickness. We call this multi-mode. And again, if you send fiber through that, what's happened? The light tends to bounce on the side walls of that fiber, up and down as it goes down there, and it is losing a little bit more of the light than the other kind, which is a more thinner fiber, which is about has a diameter of about 9 micrometer core. And that one does not bounce around so long, and this is where we use most our distributed acoustic sensing and strain measurement on. Now, there's different methodologies for looking at the light coming back or creating those lights. and we call this the backscatter spectrum. I can actually look at different frequency ranges of the light that are sent down. And distributed acoustic sensing uses the Rayleigh spectrum, which now you see here in the on the white side in the middle. It's the blue energy spectrum right in the middle. Excuse me. It has it is the strongest of the spectrums. That's the reason why we like to use it for our main measurements. So you send something down there, you send a lot of energy down there, and you can get a lot of the light back. So you can actually reach out pretty far with your measurements, distance-wise. It can pick up any strain changes. It can pick up any temperature changes. So there's a vast amount of measurement physics. Different kind of physics you can actually pick up. The second one is the Raman spectrum, which is the green one that you see here in that picture, and it actually has two peaks that go together. The one on the left side and the one on the right side. And the interesting thing of those spectrums is that one of them is temperature sensitive. So it changes now it shows a response when you actually now do some temperature changes on the fiber, and the other one is not. So by now comparing those two together, you can actually figure out an absolute temperature. So and that's the reason why we call this particular measurement distributed temperature sensing, because it can now, as I said, get you a temperature in Kelvin or in centigrade. The last one is the Brillouin spectrum, which is sitting between the Rayleigh and the Raman spectrum. So that's the orange one over here, and we call this distributed strain sensing. And this particular spectrum is sensitive both to strain itself and to the temperature. And you see it creates a temperature shift as now the fiber is going to be experience a change in the temperature or in the strain itself. So that's a relatively new measurement, and it's being used recently more and more. And you can now look at different machines, different interrogators, and actually now run those on cables. Now, as I said, those fiber optic cables, sometimes it's multiple in there, and you can actually run different methodologies, putting in now multiple interrogators. So we are going to focus on distributed acoustic sensing. And distributed acoustic sensing, as I said, what it does, it measures the change in strain along the optical fiber every meter at typical sampling frequencies of about 20,000 hertz. And again, that's what normally those machines are capable of. And the limit of those sampling frequencies are, of course, based on the length of the fiber, because what's going to happen is I send the light pulse down the fiber. I have to wait until it now travels all the way into the fiber, and then I have to wait until the last now back reflected light from the end of the fiber is coming all the way back to my interrogator for me to now record that, and then I have to wait just a tiny amount of time before I send the next pulse down. So the longer the fiber is, of course, the less pulses I can send down a second. Now, for offshore for wells in a downhole environment, those are not that long. I mean, we are talking about a few kilometers. And now, as I normally sample those with about 10,000 hertz. Now, for pipelines, as I said, it's based on the speed of light. It's in fiber optics, that's about 213,000 kilometers per second. I'm about limited to about 2,000 hertz. Now, so I am measuring strain changes. And again, those strain changes can be induced by multiple different physics. And that's what makes fiber optic measurements so powerful. Normally, measurements of any instruments in a pipeline or in a well, there are point measurements. So I might be getting a pressure sensor, I might be getting a temperature sensor, I might be getting a strain sensor, and they are very focused on what they're measuring. It's based on one physics. Temperature only measures temperature, and so on. and again, they are point measurements, so I only can have so many of those, and then I need to, based on those measurements, I need to figure out what's happening in between, and often we have to use modeling methods to now create some kind of computational model that's now where we are kind of estimating what happens in between. Now with fiber optics, we are actually doing direct measurements distributed along all the fiber, and just picking up every meter really. And those string changes, the different physical impacts on the fiber, they're proportional to the acoustic activity and or the temperature changes in the vicinity of the fiber. And again, that can be now directly at the pipeline. That can be now farther away. I mean, in pipeline flow, we can pick up signals that are multiple 100 feet away. And now in subsea wells, when I have a fiber down there, I can even now pick up stuff that's happening now 1,000, 2,000 feet away, specifically now when I start looking for seismic signatures and so on. So distributed acoustic sensing is around for quite a while now, more than 10, 15 years. Originally, the applications, it was developed for border and perimeter security. Of course, it's a military application. Then I started moving it into infrastructure, and I was doing it along roads and bridges to see, okay, what's happening over there, getting an idea what happens now when you get too much traffic on a bridge, at what point it might be failing, getting an early warning system and so on. And then I started to go into seismic profiling, try to image the ground around now around wells and so on. You can do microseismic. And then again, for oil and gas specifically, now we like to use it for hydraulic fracture stimulation monitoring. And then as you now have it over the reservoir, you can look at leak detection, production flow monitoring, and so on. And from there now, then we went into pipeline monitoring. Now it's much easier to install a fiber optic along a pipeline because now you're at the surface. It's very easy now to now dig up a little trench, now put the pipeline along and maintain it. Where now when you go into a downhole environment, it's a pretty hostile environment. It's very difficult sometimes to get the fiber down there. So distributed acoustic sensing, and generally the data comes back as a waterfall plot. And here's one example. Again, this is a hydraulic fracture stimulation monitoring example. That's the picture on the lower right. And the reason I show it, it's a very strong signal, so it's very easy to understand what's happening over there. You got your time on the x-axis. You got your distance on the y-axis now, and as you start doing something to your well, and in hydraulic fracturing, what you do is you pump down liquid. You try to now open up the reservoir by cracking it. You see actually where the stuff is going. Now you start the pumping, it's going to go into now several areas of the reservoir, and then after that you stop the pumping, and then you start your next stage. So blue in this case means now nothing's happening, and then the red thing is when you get your acoustic signal back, and you actually see where along the fiber stuff is happening, and you see the magnitude of the signal, which then relates in how much fluid or how much sand in this particular case you can put in. And again, that stuff directly then relates to any pipeline monitoring, because again, something happens along the pipeline, and those signals then can be interpreted as now whatever happens along the pipeline. So let's look at how we actually install a fiber optic distributed acoustic system sending along a pipeline. And here's a picture down here on the lower part. So as we start looking into anything moving through the pipeline, in our case specifically CO2, is being generated at some kind of point, maybe a power plant. The CO2 needs to be scrubbed out. It's going to be now put in some kind of terminal. It's going to be liquefied under high pressure, and then it's going to be put in the pipeline. There's a pump station now, and generally we are running those pipelines at about now above 3,000 PSI. I think it's about 25 megapascal. So it's pretty high pressure. we're trying to liquefy those CO2 because it's easier to transport. And now one of the things we're trying to make sure that we are getting it in mainly liquid form. So we're not dealing with a two-phase flow system, which now causes some problems. It's not always the case, but now that's the ideal condition that you're looking for in pipeline transport. So that goes into pump station, or it goes down the pipeline, or that could be now a few dozen kilometers, or it could be now even 1,000 kilometers, depending on where you're moving it. And then it goes into some kind of end terminal, which might be a storage facility, or it might be now directly going towards a well system there, where you then deposit that CO2 underground in some kind of depleted reservoir, or you might even be using it to help you in additional oil recovery by trying to repressure up depleted reservoir already and get the pressure back up, so you can now get some more hydrocarbons out. So the way that we install those fiber optic systems is, as I told you earlier, the limit of fiber optic measurements are based on how much losses I have in the fiber. Because of those inconsistencies, more and more of that light is going to be back reflected, and now less and less light is going to continue to travel down the length of the fiber. So at some point, as you make the fiber longer and longer, I don't have enough light left to actually now give me a sensible measurement. So there's just too much to length, and then the losses are going to accumulate, and then I can't see anything anymore at the surface at that point. So that's the reason why the maximum length for fiber optic, now using the regular interrogators that are sending down a ping pulse with a very, very narrow high intensity laser pulse. The maximum distance is about 50 kilometers. You might be going up to 100 kilometers, depending on what kind of fiber you use. You can have some engineered fiber that is specifically designed to now increase your now black reflected light amount and so on. That means I'm having my interrogator sitting up there. It can send out a light. It can now service a fiber optic cable about 50 kilometers long, but I don't have to go in one direction. Those interrogators boxes, they can send out light pulses into different cables. So I can actually have two cables. One goes now upstream to the pipeline. The other one goes in the other direction, downstream to the pipeline. Now I can measure about 100, maybe up to 200 kilometers with the same box. And that's how we install those. We have those boxes now every 100 kilometers, every 200 kilometers, with fiber going left and right. And there might be now, as I said, it's not a continuous fiber. Those are two different fibers. And then we got another system 100 kilometers apart. And then now you're taking that measurement and now just splicing it all together. And then you have a continuous measurement all along the fiber. So those boxes in generally, they might be sitting at a pump station if you have multiple pump stations, or they might be sitting in some kind of little shack on the side that has power. And then you're going to send those pulses. Again, those interrogator systems then need to be connected to some kind of communication fiber network, because the amount of data that distributed acoustic sensing is picking up, it's in the terabytes. Each of those machines is going to make terabytes of data. So that's a lot of stuff. And generally, we don't need that stuff. Most of it is going to be discarded because we are just looking for particular event recognition. So we are not going to do any scientific analysis in general of that, where we need all the data and we really want to look at it in detail. We are running now intelligent algorithms on that can identify those responses, and then now the answer product really is being sent towards the operator, who's going to be sitting on a computer. The whole stuff goes over to the cloud. I can now use that for data storage. The alert system runs on it. Any of those now automatic event recognition systems and analysis softwares are running on that, and then I can remotely access each of those machines and make any changes if I have to. Do maintenance on it and so on. So again, a pretty neat system. Now the way that the cable is installed differs from the way that we normally install this in the upstream sector, which means in the well going into the ground. In that environment, we actually now string the cable directly to the casing as we put it in the ground. In pipeline in a pipeline environment, we don't have the fiber directly touching the pipe. We normally bury it a little bit further away. Now this might be now 2 meters generally, and it's going to be in the ground. And there's different methodology, different ways I can, or locations I can actually install it. And now you see those different applications here on the upper right. I have my pipeline is buried into the ground. In generally, now I surround the pipe with some kind of cladding. Or I might put it into some kind of cement environment. I might now put it into some kind of compacted gravel environment and so on. And then I put the fiber. I can put the fiber on top of it. So that's the most preferred way of putting it. We call this the 12 o'clock positions, because the data that they can get back is the best quality. Now another possibility is to use a partial padding. So you put the pipe in, you just now have this compacted gravel on the bottom part of the well, and then you put the fiber into the 3 o'clock position, which means it's going to be at the same height of the middle of the pipe, just now maybe 2 meters away, 2 meters away. Again, you get pretty good connection between the pipe and the surrounding environment. So the data is not, it's not as pristine anymore as now with the 12 o'clock position, but it's still pretty good. And then you got the 5.
We're running out of time, so would it be possible for you to wrap up?
Yeah, I can wrap this up, and then you can put it in the 5 o'clock positions. So pipeline monitoring, you can do different things. One is event activity, and again, you're trying to figure out what is actually happening at what kind of distance. And those are automatic algorithms that are running and just looking at the waterfall plot of the data. So in generally now you use now advanced algorithms and maybe even machine learning, and you're trying to find out now, is something happening in the pipeline, like a leak? Do I have now a scraper? How's a scraper or pig that goes through the pipeline behaving? Do I have any seismic events, animal movements, people walking by, vehicle movements? There might be some tree or brush cutting. There might be some excavation. That's always now a danger for pipelines, because some pipeline they run over with an excavator, and now I can get a really big mess. So we are trying to figure out now at what distance things happen, and now as you get closer to the pipeline, you're getting a more urgent message to the operator that, hey, now something's really happening, and we are trying to identify the event, and then they have to react to this, and that includes leak. And now that's the one of the most important part of now taking those measurements, because we are trying to figure out where those leaks are and where, when they're happening, and trying to detect those early, hopefully before we are even getting that leak. And now there's different modes that we can do. We can do negative pressure pulse. So that's a methodology to find sudden ruptures. Now you have 3,000 psi in the pipeline. Suddenly now you have through corrosion event, for example, you create a hole, and now this ruptures, the CO2 is going to come out, and it's going to create the pressure pulse left and right up the pipeline, up and down the pipeline, very strong, and then you get now the gas streaming out, which is going to create a turbulent flow, similar to flow through an orifice, which is a signal that you can pick up very easily and identify. There's orifice noise, which says if you have flow through a hole, and generally now it's a slower developing leak. You don't have the sudden rupture, so you don't see the negative pressure pulse. You mainly see the acoustic signal of the fluid going through the hole. Then you have ground heave. Now you have fluid exiting the pipeline, and it's going to displace the ground. And now, as this is being pushed towards the pipeline, towards the fiber, you're going to bend the fiber slightly out of place, and then you can identify that, hey, something's happening over there. And the fourth part is now what's happening specifically if you do anything that develops from liquid back into gas, because it cools down pretty rapidly. You actually get a very cryogenic effect, specifically with CO2, and you can pick up the temperature changes as now you get a leak. Now everything cools down around that, and the bad thing about this now, the pipeline generally gets very brittle when that actually happens. So just to give some quick examples.
We need to conclude because we're in discussion time already.
Okay, so again, I mean, here's some quick examples that you can see how you get you can see the waterfall plots, and you can see, you can pick up the pressure wave and the acoustic signals, and you can pinpoint the leaks. Okay, so I wanted to thank you for listening to this presentation, and specifically I wanted to thank Midstream Integrity Services for some of the data and the pictures that they provided.
Thank you, Marcel.
Thank you.
So this was quite interesting. I would like to invite Marcel, of course, please stay, Gareth and Monica to join us for the discussion. It's nice to bring in the experts in the areas that we don't know. A couple of years ago, we had the first workshop on net zero, and in the discussion, we were talking about how dangerous is it to have a leakage in a CO2 pipeline or situation after you had storage CO2 in the subsurface. And the comments from the non-experts were it cannot be that dangerous, right? Because CO2 is not dangerous to life. You drink it in bottled water, it's greenifier, etc. But today we had the experts actually talking to us, and it was very interesting to listen to all of you. And Monica, you did mention about the toxicity hazards and the chemical reactions. And that's quite interesting because one of the challenges with CO2 sequestration is the social license to operate. And quite often we get situations in which people are very happy for us to do CCUS projects as long as it's not in their backyard. So that was quite interesting. And of course, then Gareth, you talked about corrosion and the effects of actually all these reactions and the parts that we don't know, which is also quite interesting. I would have thought, because we had decades of experience with CO2 in pipelines for enhanced oil recovering programs, that we actually had a little bit more knowledge, but perhaps it's different what we do onshore versus what we do offshore. So this was quite interesting as well. And I'm also curious about how large are these cracks, how early should we detect them, and how big they are. And then of course, Marcel, you bring this back to remote sensing, which is what we in this community are more familiar with. So I would like to start with this comment, the conversation, and I will invite Monica, Gareth, and Marcel to give their initial thoughts about this session. And please, anyone who has a question, please raise your hand and we will invite you to ask the question directly. If not, we will entertain our guests with conversation.
Yes, yeah, I have a question. It's more related to the commerciality and the commercial concept of CO2 capture and storage. And I think this is sort of touching to all of the presentations that we have here. So what I was wondering if anybody had an experience of being involved through commercial contract negotiations, which parameters of CO2 are the most important ones for commercial negotiations, for instance? So for instance, let's say impurity could be one of them, and then probably there is some sort of a rate for that, maybe pressure, temperature, another one. Are there anything else, or can you discuss between yourselves, or does anybody have a real life experience with that?
I think we have a real life experiences. I just don't know how much I can share. If I should reflect to the extent I think maybe it's okay. I think since there is this, it's important to find the balance, right? Like I mentioned, between the cost actually of purification that lies on the emitter's side as a responsibility. Therefore, there is this importance of finding the balance, because not all the technologies can deliver to specifications, let's say, that we might want to have in the pipeline or in a ship. And what that means is that if the emitter does not currently have the technology on site that can deliver the standard for the CO2 spec that, let's just say Equinor would require to have, then of course that can affect the emitter, and that will affect them financially. And of course that is then connected to the different impurity levels, also possibly a vapor return and so on. So yeah, I think the impurities are quite significant part of many discussions with customers.
Anthony, you had a question. Do you want to ask it?
Yes, I do. I'm just wanted to make an additional comment to that last question. It's a very interesting one. I guess a lot of these carbon markets are not really fully established, from trading from emitters to the storage providers. And this question might be a really good one to remember and ask tomorrow when we're talking, sorry, not tomorrow, in the next session, when we're talking about the business context. That may produce some additional, more interesting conversation. But I also did have a question, if I may, while I'm here. I had a question for Gareth. Very interesting work you're doing on better quantifying the corrosion performance, especially under different conditions. And I guess, well, maybe I missed something, but this is all in discussion of certain grades of steel and maybe stainless steel. But has there been any work or even experience on using coatings within those pipelines? I'm saying that because I guess you have to use steel for mechanical strength.
Yes.
But I'm imagining you could coat the inside of the pipeline with plastic or certain inhibitors to better control that corrosion performance. And I'd be interested to see what you have to say about that.
Yes, I mean, that's certainly an option, but of course, it's the expense of the coating. So again, it's a trade-off. I think the industry is hoping that it can get away with using uncoated carbon steel because that's the cheapest option. It's well established in conventional oil and gas pipeline transport. Adding a coating is going to significantly increase the cost. There's also an issue with coatings in that they're great, but they tend to be very weak at the point of failure. So there's no such thing as a perfect coating. You're going to have damage during installation. You're going to have damage, particularly from entrained particles and erosion of the coating. And where the coating fails, all of the bad things will be concentrated. And that can often lead, instead of to a general wall thinning, to a catastrophic accident. So you've got to also take that into account.
Fair enough. Okay, thank you.
I could maybe reflect also on the second part of your question, Anthony, because you asked also what about possibly using polymeric pipelines or materials that are plastic within the pipeline. And I guess here is then again the question, if we have precipitation or falling out of the acids in a very, very concentrated form, we would have to also evaluate what impact do they have, and we are doing that, of course, at the moment. We just don't have clear answers yet. What impact does it have on this polymeric material? So it's not, I don't think so we are there yet, but definitely it's something what is considered.
Stefano, do you want to ask your question live? In the meantime, can anybody explain a little bit more about the differences between, besides obvious, onshore and offshore? Is it materials that are different? Is it the impurities that have been in use in enhanced oil recovery that are not there? What is that makes the biggest challenges to understand?
I mean, between offshore and no, the pipeline system. Now, when we install those systems into the ground, to put carbon into the ground, or now get our hydrocarbons out of the ground, it is the materials that we use are based both on the high pressure and temperature in there, so it needs to now withstand that, as well as now the very corrosive or very I mean, there's a lot of nasty stuff in there now, like H2S, for example, that can easily now develop. And now if you get that up back to the ground, now you can, I mean, it's very, very, very poisonous. Now it takes out people relatively quickly, right? So the materials that we use are now made to withstand it. And of course, now every time you do a project, you are trying now to use materials that are fit for purpose now from a cost perspective. I'm not trying now to put stuff in there that is so corrosion resistant now that now my economics now are going to topple over. The same thing is what you have really for pipelines. Like, for example, now putting in on plastic power plants now is going to be very expensive, because you would have to make them withstand the pressures that you have during the transport, because they're highly pressurized, right? So that would make it very, very expensive. Or, for example, now the other part regarding now trying to clean up the stuff that you put into the pipeline, to make sure that you don't have any other chemical components in there that might create corrosion, right? Yeah, I can do that now, but it gets exponentially more and more expensive, right? So yeah, I can make it now almost perfect, but now at that point, now you're going to be so far down in the red that it's going to be unfeasible, right? So you always have to see now what is going to be the trade-off between now still making money, because now at the end you have to make money, right? Yeah. And now still being able now to deliver this now within a safe and feasible environment, right?
Yes, and economics is quite important. So I mean, in one case you are storing CO2, and yeah, in the other case you are actually extracting oil that is much more profitable.
Yeah. Now the thing on the upstream side, which means I'm downhole, right? When I'm in the reservoir and I screw something up, and now like I'm corroding through a pipe, it's not a big deal, right? Because I'm in the same reservoir. I might now I might change my production or my injection scheme, because now instead of something going over in one part, it might be going a little bit further down, right? It might not be now what I originally intended, but now it's not going to now create an environmental disaster, because I'm in the same reservoir level, right? When I'm up in a pipeline and something corrodes through and now something spills out, it's a disaster, right? It can create now really harm to the environment. It can create really harm to people that might be going down there, because a lot of those pipelines, they might be now going on a city, now they might be going on a village or something like that. Now they start busting now, and now we're going to have a mess.
Thank you.
So it's easier now for the pipeline stuff than it's easier for the offshore for the downhole environment.
Thank you, Marcel. Stefano, would you like to ask your question?
Ready. Can you hear me?
Yes.
Okay.
Hi.
First of all, great session today. Very nice presentation. So my question is very simple. So since a DAS system is a measurement of a dynamic strain on a fiber optic cable, is there any chance for a DAS system that will sense the strain at earth-tide frequencies? And if it is so, do you correct for those effects?
That is a good question. I'm honestly not sure. I mean, with what we do with DAS is we are measuring within the Rayleigh frequency spectrum, and again, I mean it's a relatively narrow band that we are looking at now from frequency band spectrum, or now, as I said, from wavelength spectrum. And again, it picks up changes in strain. It does not pick up the strain itself, right? It does not measure absolute strain. It only measures.
It should be a measure of the dynamic strain. So I would expect some type of effects.
Yes. But you're right. I mean, you're going to see that. You're going to see.
And
those
again,
effects.
this is superposed to some temperature effect, depending on the application, on the environmental settings, and etc. Maybe you have a kind of superposition with the main, again, diurnal or semi-diurnal temperature effects.
Yeah, we are trying. I mean, when we look at the data, we are trying to figure out, of course, which kind of physical which kind of physics created those signal effects, right? And they're all superposition. Now that's what makes it sometimes difficult. Right? Now there's temperature effects in the low frequency band. There's going to be now the acoustics now above. Now could go from a couple of hertz all the way up to now thousands of hertz. And then, of course, now there's rock movements, there's now the seismic and everything else, pressure effects in generally. So now putting them apart, specifically the temperature, is not easy. So we are trying to use additional measurements to now try to subtract temperature effects, for example. So I can run DAS, but if I have a DTS system too, now running on a cable that's right next to it, then I can take those temperature effects and try to calculate those out. And specifically, you see those in not only DAS systems, but often in the strain systems, because you got now again the temperature effect over there. So they in generally run both the DSS as well as some kind of now temperature measurement system, which is like a DTS, and they're trying. You have to calculate us out to get a pure strain, not one that's going to be now. Not one that's going to be now tainted by temperature effects.
Okay.
Thank you. Royan, do you have a question?
Yes, I have a question to Monica and Gareth about the impurities of impurities in CO2, and I would like to know which one is the most critical to handle and maybe challenging for the capture side to handle it, and we are more restrictive to control those type of impurities. Gareth touched upon water, but I would like to know about the other elements and see to understand which one is more important to control.
Monica, would you like to go first?
I can do. Yes, I think water is very important, but the component that is also really important and actually acts sort of as, you can say, accelerator in a certain sense is nitric oxide or dioxide. And we can see that this is a component that actually accelerates the reaction to nitric acid. Of course, this component is not always an issue to each of the emitter, because not every emitter has NOx in its emissions, but it can be challenged to certain emitters. And also, of course, oxygen is critical as well. And I guess the oxygen is present in not all the emitters again, but it's present in very many. And I understood from the capture experts in Equinor that this is the component that is also very, very difficult to clean, and it costs a lot if you want to do that, because you have to change your technology. And then if we don't think about chemical reactions and corrosion, there can be also a challenge having PEG or MEG. if the specification on TEG and MEG is very low, especially on TEG, you can have a challenge to how to dry your CO2 to deliver to the spec and not have, for example, the tech that will carry in with the stream. So yes, I think these are the main ones besides water, NO2, oxygen, and possibly TEG that can be a challenge.
Then maybe I can ask Gareth about the impact of pressure and temperature on reducing the impact of these impurities. Are we able to reduce the corrosion rate with changing the pressure and temperature?
Well, it's a complex. Just before I answer that question, I would like to link back to Adriana's question about enhanced oil recovery, because Monica's given a perfect answer to the key impurities question. And the reason we don't have the experience from the decades with EOR, particularly in the US, is that those key impurities, particularly SOx, NOx, and oxygen, are not present in the EOR stream. So this is all new for most operators. To go on to the temperature and pressure issue, really we are quite restricted as to the temperature and pressure operating window. And the key issue is condensation and acid dropout. So there's a certain solubility that's associated with the composition and the concentration of each impurity. If we drop the temperature or pressure too much, we're going to get more condensation. So really, we're quite limited in what we can do operationally. It does come down to cleanup versus long-term integrity and the other things that Monica mentioned.
Thank you.
Wish we could continue with this conversation. Next time we invite you, we will have to allocate more time for the discussion, because obviously we need to learn a lot from you. Thank you very much. If you would like to leave your email address, if you want to, please do it in the chat box so that people can ask you follow-up questions. And I would invite everyone to a splendid 5-minute break before we come to discuss more on the high-level context, cost, business, regulations. And yeah, I'll see you in 5 minutes. Thank you.
Thank you very much.
Thanks, everyone.
Well, welcome back, everybody, for the second part of today's sessions. We'll cover the business context of CCS, chaired by myself and Adriana here. I'd like to introduce the first talk of this session from Will Bradbury of TGS, looking at the overview of CCS activities and future insights. If you please, Will.
So as you said, it's within the business context of CCS. So I'm going to give an overview and some insights really on activities around the world. But perhaps as this is not necessarily a fully technical talk, my background is actually as a structural geologist, first 10 years of my career. And then the second 10 years has been in seismic project development. What that really means is that I'm very interested in the technical component of carbon storage, but I'm also very much interested in how the CCS market is going to be developing over time, what kinds of projects are going to come online, and so on. So what I'd like to do during this session is share some of the learnings that I've had and the work that we've been doing in this area. And really talk about what's actually happening in CCS around the world, what the future is. And then, as I'm in the seismic business, and that being the context here, talk a little bit around some different monitoring technologies and the considerations in those monitoring technologies. I think it's fair to say that there's still a lot of dialogue going on around what is actually needed. So I'll propose some potential technologies, and then hopefully we'll get into the discussions a little bit later. So it is a talk of more or less two parts. So global CCS activities, what projects are happening around the world, the different support mechanisms or incentives in different regions, and then what that might mean in terms of where different projects grow in the future. And then in the second part, we'll talk about some of the seismic monitoring technologies, how that is progressing into the future. There's obviously been a number of surveys, baseline surveys and things done around the world, but particularly in Europe recently. And we can talk about what is the purpose of those, and then push that into the future perspectives of what does the sort of geophysical industry need to deliver into CCS monitoring, and what would be the requirements of us, or as geophysicists and so on. So I'll start off with a map that I'm quite sure everybody has seen a number of times. This is from the Global CCS Institute. And what you're looking at here on the left-hand side, all of those red dots, those are operational facilities. We'll move on to the right-hand graph. That's where you're seeing new projects coming in line. But back on that left-hand graph here, you can see all of the operational facilities around the world. And you can see more or less where they're clustered, certainly in North America, Europe, a little bit of activity in the Middle East and Australia. Nothing really in Southeast Asia at this point in time, but we'll come on to that a little bit later. So a lot of these existing operational facilities are actually linked to quite low cost to capture industries, and that's things like natural gas processing, ammonia and ethanol, and that's the source of the CO2 that's going into them. What you're also seeing on the left-hand side is the number of projects, operational projects, prior to the Inflation Reduction Act, 45Q, for instance, where tax credits are being offered for the storage of, or capture and storage of CO2. When we go to the right-hand side, I believe this map is also predates some of those incentive schemes. We're going to see, I think, some significant growth as regulatory environment matures, as incentivization or subsidy and those different aspects come to fruition. But what you're seeing is a lot of bit different role in different regions. So Europe, for instance, clearly has quite a focus on industrial decarbonization. Southeast Asia, those new projects that you see popping up, a lot of those are actually linked to natural gas processing and converting what could be described as disadvantaged gas into something that can be brought to market. A bit of an overview here on the different systems that are working in different parts of the world. So over in the US, if we start there, a lot of projects in advanced development. There's early development projects, there's in construction, and as we saw previously, there's quite a bit in actually operational at this time as well. I think we're going to see that this will increase now that the Inflation Reduction Act is in place. 45Q has actually been extended as well. So those tax credit schemes are driving new projects across the region. Very high level overview of what that might mean. You can see you do get a tax credit, $85 a ton for storage, $60 a ton for enhanced oil recovery. And then we'll drop into this one on the next slide, but $130 to $180 for direct air capture with CCS. If we move over to Europe, it does certainly appear on the surface to be quite a more complex system, but obviously subsidies are playing a role here. The emissions trading scheme, we've seen certainly development in the price of that. And then within Europe as well, there are national level taxes, there are different credit schemes and so on. So we won't go into the detail of that one. There are a vast number of those different projects. When it comes to the Asia Pacific region, then perhaps not as mature as the other parts of the world in terms of the regulatory environment or credit systems, but they do exist in this region. But I think what we're actually seeing in that region is more the development connected to LNG. So you do see projects, certainly like Gorgon. I think most people are aware of that. Gorgon is an offshore development, and then the LNG on Barrow Island. And then when we get to Moomba, that's the Cooper Basin project, again, connected to LNG. So we're seeing different types of projects in different regions, and we're also seeing different incentivization schemes in different regions. And those are all going to have an impact on how, or the rate at which different projects are developed. If we go to the next one, what I've pulled out here is really the cost to capture, so capture cost. And these are numbers published by the International Energy Agency. You know, they will change over time, of course, as different technologies are brought in, and innovation happens. But I thought it was worthwhile putting that in with the Inflation Reduction Act, because you can see top of the list there, as I'm sure almost everybody would expect, is that direct air capture is one of the most expensive capture mechanisms that we have. And then the IRA there is designed to incentivize innovation in that space to bring down the cost of direct air capture. If we take a look at the next three on that list, then we're looking at power generation, we're looking at cement, iron and steel. So very much industrial decarbonisation, and that has a slightly higher cost to it. I mean, there's been certainly some interesting talks in the previous section, you know, in terms of the specification of CO2, and I think that as well is going to play a role in terms of how quickly some projects can be developed compared to other projects. If we look right down at the bottom of the list, then you have natural gas processing, and that's really what I'm speaking to here. And if we look at the different projects that are actually in operation today, then you can see, well, perhaps a little explanation of this graph. You're looking here at the CCS facilities that are currently operating or are operating between 1980 and 2021, and the million tons of CO2 sequestered or stored. So 1980 all the way through to 2021. And what you can see in this light blue color here is the number of projects that are generated from natural gas processing. And that's certainly something that I think we as a wider industry are well aware of, that this is one of the main areas where CCS can play a significant role, certainly in support of the hydrocarbon industry in terms of decarbonising LNG and so on. So this is really in reference only to the US here. So in around 2008, I think it was, you had the 45Q tax credit came in, and then you start to see more projects growing. Inflation, and you see that further into 2021, Inflation Reduction Act post-dates this graph. So it remains to be seen, but we've certainly heard a lot of noise about that area as well. So a couple of examples just to explain what those projects look like. These are LNG projects. This one is a schematic from the Chevron website on an LNG project in Australia. This is Gorgon. What's interesting, I think, about some of these projects is that the market for the natural gas is in Asia, and I think in particular in North Asia. And what you see is some of those drivers for decarbonised LNG coming through from governments who have net zero ambitions, and so want to reduce the carbon footprint of LNG coming in for power generation. And so on. So the export market is providing a demand in this area. What's quite interesting also, I think, about projects like this is it's a single E&P operator, or a consortium, I should say, a group of E&P companies who are operating it. So I think a lot of the discussions around some of the complexity with different projects, where all of the emitters essentially have different specifications of CO2, and creating the sort of the administrative load and communication of technology and so on is quite, or could be, more of a challenge for these kind of projects, where you're looking at the decarbonisation of onshore industries. And many more stakeholders, I think, is probably the key thing to say in this regard, and they will all have different CO2 coming into the system. And we do see that as two, or I do see that as two different types of developments, and we'll see how those develop, this sort of hub and spoke versus the LNG developments run by small groups of experienced E&P operators offshore. So a little bit of a look towards what will happen further. So going back to the graph on the existing operational CCS facilities, and I'm sure some of the other speakers later on in this session will talk about this a little bit more. But we see these sort of gas-linked projects. Gorgon is one. There are others in Europe around Sleipner, Snøhvit, Moomba in Australia, and so on. There are also many more. These are single point-to-point type projects from emitter to storage site. When it comes to the growth that we see linked to industrial decarbonisation, these tend to be much larger consortia, or at least there's many more stakeholders in projects such as the one I showed previously, the East Coast cluster. Multiple sources of that CO2, and I'm sure there are challenges related to optimizing transport distances or other sensitivities, and so on. And I think probably there are well, this is probably one of the causes for why you have different incentive schemes in some of these different areas, in that you need to create the market for it, and then those projects need to be developed over time as well. So really, that's an overview of a very high level and short overview of what's happening around the world. I think these hub and spoke industry adjacent programs, and then these LNG projects, and they will have different growth mechanisms and different incentivizations. I mean, for example, the LNG will grow as that LNG market grows as well, and hopefully that will grow in parallel. And we do see growth in that market. So I think there is going to be an increased need for monitoring technologies going forward into the future. So that's setting the scene really for talking a little bit about seismic monitoring technologies. And we'll go through a few of those over the next few minutes. Now there are plenty of discussions, of course, around things like containment and conformance. But I think, as well as sort of seismic experts, we need to consider as well, you know, what is really needed from seismic data in particular to demonstrate containment. Now, there are lots of other technologies available out there. I'm really, for the course of this presentation, just considering seismic technologies. But what's really needed to demonstrate containment of CO2? Do you need to see the CO2 in a reservoir, or do you need to see the lack of CO2 elsewhere? So it's sort of a direct versus indirect monitoring scheme. And a very similar question in terms of demonstrating conformance with model forecasts. To what resolution, perhaps, is a question that we could ask there. So going into current seismic technologies and some of the future thoughts, there is out there, if you want to take a look, there really is a growing database of published MMV, measurement, monitoring and verification plans, along with a large amount of discussion at conferences. Different regulators are going out there commissioning studies from consultancies and so on what needs to happen or what should happen from a regulator perspective as well. But I think there are some regulators talks a little bit later on. We also know that baseline surveys are being acquired. There's been a few in Europe over the recent year or two, and indeed some of them have been going for a lot longer than that. We'll see how those develops in time. Obviously, there are some areas which have a significant amount of experience. You know, Sleipner is one example for that. In other areas or other developments, these are more sort of first of a kind, particularly for either the operators or the government or the regulator and so on. So if we take a look at that, the toolkit that we have as a geophysical industry, it's significant, it's very big, and I think we need to ask ourselves why. So if we come to this one, then very much, I think, driven by the oil price. So the blue line here is really charting the oil price, and then the top section here, and I won't go into too much detail here, but you see the application of seismic technologies, and here I'm using streamers and really referencing Norway, where this data is available. But you see a lot of these technologies that were theorized decades or more before are actually coming into application during increases in the oil price. And we'll see how the same thing develops in terms of CCS as the tax credit schemes, incentives, and things like that develop for CCS. A little bit, first of all, on seismic technologies. So obviously we have existing seismic data around there for regional screening, site suitability, new baseline surveys, and then potentially early warning systems. And we heard of some talks about some of those yesterday as well. And then the repeat, the full field 4D repeat, which comes later. I think as we move through that system, then and talk really about baseline surveys here. If you have a short duration survey, then you can have a slightly higher run rate on your cost and potentially a higher environmental footprint with that as well. When it comes to early warning systems, you need very long duration monitoring, which means you need a very low run rate, and you probably don't want to accept a very high environmental footprint. Then of course your scheduled or your 4D repeat will be the repeat as well. So into that box, we put a number of these different technologies, really baseline surveys, DAS VSP, XHR, it's a short streamer solution. You have long streamers, you have nodes of various different configurations. In early warning systems, then we might talk about in-well fiber as a passive sensor, or as a DAS VSP application where you have an active source. And we heard from the folks at Spotlight yesterday on using a very small number of nodes. Then we move into the repeat. As far as I'm aware, in terms of what's been done, we obviously have seen a number of longer streamer applications done for baseline surveys and so on. We've seen early warning systems, so fiber optics are installed many places around the world connected to oil and gas. Current projects, so just pop back. So DAS VSP, I know that we have a number of current projects. We've also been out in the North Sea and we've tested the short streamer XHR solution. You heard about Greensands, where we provided some nodes yesterday and what's moving in that. And then, of course, we've seen scheduled surveys, long streamer repeats as well. But I think as we learn more and more about this, about these monitorings, how we apply those technologies, then we're going to be able to refine certainly diagrams like this. And I'd certainly welcome thoughts and considerations on what else should be added in here or what should be removed and so on. But just to bring us to a close here, I think in summary, hopefully that initial business side there, we certainly see that CCS is growing and it's growing across the world. A variety of different mechanisms causing that growth, but there is growth coming forwards. The drive towards industrial carbonization in Europe is certainly very, very strong. That's also the case for the US. But CCS also has a role in the decarbonization of high CO2 gas fields and so on. So we'll see that come online as well, and we'll see how quickly that develops. Current seismic technologies, they certainly work. We've seen them work in many places, but I think it's perhaps a question of how do we apply these? Do we combine some of these? Do we adapt some of these to the market as it is today? And with that, I will thank you. I think I'm just about within time, Anthony. Hopefully that's all right.
Oh, perfectly done. Well done. Well, thank you very much for that. I'll introduce our next speaker in the interest of time. We have Anders Niemann. I hope I pronounced that correctly. From the Norwegian Research Center, or NORCE, talking to us about full chain CCS activities. If you please, Anders.
Thank you. We have a lot on our heart today, many of us, and I'm really honored to be here and speaking to you. Okay, yeah, well, I'll just jump straight through it, and I'm going to go through some examples of full chain CCUS and activities that we have performed here in NORCE and under the lead of Roman Berenblum, and I have enjoyed working with him in a series of portfolio of projects that we're dealing with business case developments and value chain analysis and techno-economic analysis, and it's been a few years of experience that I've tried to condense into this presentation, and that's been kind of a challenge the last few days. So I have a lot on my heart. So just first, we are committed to the UN development goals, and of course, curbing the climate change is really a key for me personally and for our institution. The global emissions are all-time high. The oil and gas recovery is all-time high, and of course, the Norwegian sector in Norway, the emissions are approximately the same as in 1990. And we know that a stable climate is a climate where the incoming radiation equals the outgoing and the reflected radiation. And we learn. I always read the physics.org as a physicist. We read that the greenhouse gas emissions are all-time high, and we know that this leads to an energy imbalance of approximately 1.4 watt per square meter, which equals 9 Hiroshima bombs. Was it one each day? Was it? So there are massive energy surplus, and of course there are different reasons for it, and CO2 is one of them. And we know that this leads to an increased atmospheric temperature, ocean warming, and melting of glaciers. And the questions are what the consequences are of these. So we learn a lot of this in the IPCC reports and the Paris Agreement. And this session was called something with net zero society, and I think that we should address what that really means. And it means that basically, when given the longevity of the CO2 molecule in the atmosphere and the prolonged nature loss, making the longevity even longer, we know that each time increment we need to have a net negative solutions that equals what we release. And if you delay curbing the emissions and we need to take the climate back into a stable zone, we need to prepare ourselves for the restore society that would come after the net zero society. We are not there yet, but we could end up there because we have natural tipping points. So, and of course, CCS is and carbon management is really important in order to meet these requirements that have been agreed upon and signed by practically all nations. And we're dealing with costs now and perhaps benefits for the future. That's the concept. And just to understand the anthropogenic CO2 in the Earth's atmosphere, it's important to know that we can avoid increasing, but this is not the same as reduced emissions that we have today. And it's kind of painful because we need to stop doing things, right? And that's not really in our heart, and we don't really have any technology for doing that. And so it's really difficult. So we're going to continue to emit, and then of course we need to have a net negative solutions from the atmosphere or from the oceans. And this could be technology-based solutions, and of course we have the nature-based solutions. Big chunk of those, and of course they can be nurtured and facilitated. Let's say reforestation of Sahara, right? Could be something. And here we see the role of CCS when it comes to carbon management. Dealing with the energy transition. Well, if you look at the history of energy use, we have traditional biomass here in the bottom, and coal and oil coming on top of it. It's basically molecular based. And once we find one new source of energy, we basically combine that with increasing the previous ones. So we have had an explosion of energy in the last 250 years or so. But there's been a dawning green shift there the last 25 years ago, and we are entering now the green energy shift. So what does that mean? Well, we cannot really rely on increasing biomass. I saw that yesterday, and I don't think it's realistic because we have a nature crisis to deal with at the same time. We could have reforestation. We need to phase out almost all fossil consumption, fossil sources. And of course, what we're left with needs to be compensated by CCS. When you read these pathways towards net zero society, this has been rising. 2 years ago, we talked about 5,000 million tons, 5 gigatons. CCS. Now, latest has they are doubling that to 10 gigatons per year of storage. And when it comes to the electricity, we're going to boost it, and we're going to have a reduced consumption and efficiency gains. And is this really possible? Well, yes, I would argue it's really possible. 75,000 terawatt hours per year for 10 billion persons is, if you break it down to the persons, it's 7,500 kilowatt hours per person, which is 20 kilowatt hour per day per person. So it's entirely possible. So we can do this. The question is if we want it. And so basically we have a build-out problem, but we also have an avoidance problem. The build-out problem, I think, is fully doable. Avoiding, we don't have any technology for that. Then we deal with regulatory measures and, of course, social engagement, social activities being much more important. So in order to facilitate compensating measures, we are going to go through now 3 examples of value chains and business models that we've developed. So the first one was in the EcoBase project, where we were establishing CO2 value chains for enhanced oil recovery in Southeastern Europe. And basically, it relies on 2 premises. First, that CO2 is the only industry that can uptake, let's say, 1 million tons per year in that order of magnitude. The premise number 2 is that it is a segue for the oil and gas industry from producing oil and gas to using CO2 to create experience and to gain experience and getting a profitable business case by selling a product, and of course moving on to a permanent storage at later time within the same depleted oil and gas fields. So we went to Romania. We talked about we talked to the oil and gas companies there, and there are 2. We were looking into 2 coal-fired power plants. They have a really long history of oil and gas production in Romania, and basically we were evaluating decision alternatives when you're dealing with the oil company that could meet up with the coal-fired power plants. So we evaluated the outcome of these decision alternatives. So basically, they could continue as of today, the do-nothing case, which would give you profitable going forward when we include all the costs, including ETS, etc. That has exploded since then. Or we could have a system where we develop the field and we have a full field immediately, or a pilot, and then go to full field development. And then we projected, we calculated the oil production as function of CO2 injection and like the CO2 intensity. And we generated estimated monetary value of these decision alternatives. Or we also discussed, also went to Turkey, where we evaluated the Batı Rahman oil field, which is a heavy oil field from a carbonate reservoir. It's the biggest oil and gas field, oil field in Turkey, and they have been had a primary production period until the 1980s, 84, where they discovered a Dodon, a natural CO2 deposit, 70 kilometers away from the oil field. And they developed a pipeline between these 2. This is not pure CO2, and it's been running for 40 years. But the problem they're facing now is that Dodon is near depleted. So they, of course, they started to recycle and re-inject the CO2 at the production site. But still, they always lose CO2, so they need more CO2 to have this oil field up and running. So we went through this, and there's a cement factory here in Kurtalan, and then there's an oil refinery south of the Batı Rahman oil field that we were working with to also to develop this decision tree and evaluate the monetary value for the different alternatives. And basically, there's positive net present value, even from the business as usual, if you have the refinery capture, refinery and cement at different times. So this basically gave us some confidence that we could work with different players in the field, and we could go forward. We also have friends in the Czech Republic where that we worked with before, and we recently developed a project. Well, recently, it ends next year, where we want to mature an existing oil and gas field to become a CO2 storage pilot. This field was discovered in 2001 and has been operated by the MND oil and gas field. So and the premise is basically here that having storage available, well, this is a fundament for carbon management in any CO2 intense region, because there are lots of CO2 emitters placed around this in this region. And we used this EU storage directive deliberately to generate the work packages in this project. There is a lot to say here, but my heart, closest to my heart, is geomechanics. So I'm going to focus, I'll say, give you some things here. But of course, geomechanics, the illustration is basically that the geomechanic work is used in all other work packages, both when it comes to geological model of the storage complex, dynamic modeling and simulations, what kind of requirements, pressure domains can we operate safe within. We are working closely with geochemistry. How does the chemical reaction lead to mechanical changes? Risk assessment is obvious. And of course, we work together with the monitoring plan and of course the scenarios for future site developments, because we are constraining the total injected CO2 and basically how much of it. I'm going to show you this now. But of course, there are cross links in all other directions here as well. We are basically here at the border between Austria and Slovakia in the Sarošice field, and we are looking at the Flysch belts in the Vienna Basin. We are targeting the Jurassic formation, and here you see the fluid displacements, originally oil, gas, and water, and then it has been producing for a while and depleted, and the gas cap has expanded, and the oil zone has lifted up, and it's approaching depletion, and we're looking at how to use this asset for CCS. A 3D picture of this thing, and we are mapping the different formations here, and we are determining the strength of these rock types. Based on the oil and gas company, the seismics, and the geological model, there are no weak planes and faults crossing through the main storage unit. So when it comes to geomechanical assessment, we needed to rely on the rock strength itself. So basically you do that and you evaluate in this tau sigma space, like where you have tau is the shear force and sigma is the normal force, and you have these Moore circles, and you take the tangent of those and you calculate the stresses needed to break the rock. And then we estimated what the stresses are in the field. And when you combine the strength of the rock here and the stresses, the possible stresses, there are some uncertainties there. Well, it looks all good, all safe. We can just go along. But then we were interested in what happens when you start to re-inject and cool down the reservoir. So then it's not that simple when you're doing it in tau sigma space. Then you need to do it in PQ space, because previously the stresses are here shown as circles, and in QP space the stresses are shown as dots. And Q is the deviatoric stress, the stress differences from the principal stress differences, and the mean effective stress is basically the average stress minus the pore pressure. And when you repressurize, you reduce P prime. Basically, you push the stress to the left, the point to the left. And if you cool down the reservoir by delta T, you reduce the side stress. Given that it's weight dominated and it's constrained on the side, well, then we can calculate the side stress reduction. Basically increasing Q and reducing P further. And when we do that, and of course, all of these factors have been experimentally derived, all of them. And when you do that, you see that cooling leads to a shift upwards. Repressurization brings you to the left, and the combined effect, you can count the number of incidents because we are sampling from probability density functions. We can calculate the number of instances that leads to failure. And then we can develop these phase diagrams where the probabilities of failure is calculated here. And of course, with regard to reservoir pressure and injection temperature. And of course, combining the failure probability with the risk appetite is important when you want to assess the injection rate. If you need any warming up of the CO2 before you inject. And it's also important to determine the storage capacity. So, and we made here a model that's that was matching the uncertainty in the field. So how this is integrated to the whole system is what we are dealing with in the strategy CCS. And I see that I'm running out of time. But the purpose basically here is that we made a model that evaluated scenarios, which is a future pathway to a series event. It's a point estimate. And we use this to have regional comparison of 8 different storage regions in Europe. And it enabled us to quantify the consequence of modifying the concrete and practical build solutions. And it forced us to agree upon some basic principles for the CO2 CCS economy. It's basically built on scenario network graphs where we connect storage units, hubs, emitters to each other, and we calculate the capacity of each unit, each segment of this network and each node, the storage location, emitter, and we get to regional key performance indicators on energy use, capital expense, operative expense, and the build time. And we have different transportation units, and it's quite an achievement, I think. And it also uses what we call global inputs. I'm out of time. That goes through the whole analysis, and we are able to generate here the KPIs for the different units. So with that, I thank you, and I have a lot more to share, but let's see how the discussion will end up. Thank you.
Thank you very much, Anders. Yes, in the discussion time, we can probably expand on some of these ideas and continue. But in the interest of time again, I'd like to thank Anders again and welcome Kristin Harberg from Gasanova, who's going to talk to us about technology focus for industry and research. If you please, Kristin.
Yeah, my name is Kristin Harberg. Thank you for introducing me, and I come from Gasanova. Gasanova is a state-owned enterprise that was established in 2005, and it should advise the Norwegian government on CCS through the CLIMIT program, which I will talk more about, the technology center at Mongstad, which is the test facility, and the Longship project that will set sail next year when they start injection into the underground in the North Sea. It should also facilitate development of technology and competence to ensure cost-efficient CCS solutions, and that's where the CLIMIT program comes in. We support in CLIMIT both standalone projects and also projects that run for longer periods and that follow naturally in the development to higher and higher TRLs. We'll talk a little bit more about that split later, but we're, for example, very proud of this Aker capture technology project that has run since 2005 with the test of 100 different types of amines at NTNU and Tiller in Trondheim. And then they ended on the amine that Aker Carbon Capture are using today, and it was further tested at TCM, and then they built a mobile unit that is now used, tested and further developed at Norcem, and is then also part of the Longship project. And in addition, we have, of course, supported many other projects in both capture, transport, and storage domain. So the CLIMIT project program is a national program for research, development, and demonstration of technologies for CCS. It's divided into the Research Council of Norway and Gassnova. And as you can see from this figure here, if we focus first on the blue square here, you have with increasing TRL, you go from Norwegian Research Council, which covered low TRLs with R&D and laboratory work, over to Gassnova supporting projects into the pilot and demonstration phase. And all along with the increasing TRL, you're also increasing, or we wish that there is an increasing in the industry participation to show that the industry is really interested in the technology, that it has a life after the project has ended. Then outside the square, you can also apply to other funding agencies. You have the ACT, Accelerating CCS Technologies, which is a multilateral partnership on research and development and innovation that is now gradually transferring into CETP, the Clean Energy Transition Partnership. And it is CLIMIT that handles the Norwegian parts of those international projects. Then you have Enova that can support projects. They're not so much in the transport and storage department of supporting, but more into the capturing parts. Then we have something called Green Growth, which is more a deal to strengthen and develop the coordination and cooperation on green growth. And it is run by these 5 companies here, Gassnova, Siva, Innovation Norway, Research Council, and Enova all together. And then you have Green Platform, which is run by these 4 above here. And they're more on the innovation side of projects. So there are several different ways to get funding within Norway, but also in international projects. So what kind of projects can get support? You have idea studies. They're like smaller studies to grow the project into perhaps a larger application. And the maximum support there is 200,000 Norwegian kroners and 50% of the total cost maximum. Then you have technical economical feasibility studies and support for testing technologies on pilot scale. Those are the 3 main types of projects that we give support to. And normally it's 50% support, but the ESA regulations are the ones that give the variations over here, depending on if you're a small company and what kind of partnership, etc. These are figures from last year, and so CLIMIT R&D at the Research Council, they had 50 projects with 145 million Norwegian CLIMIT kroners in support. And the total budget for the projects of 20 million Norwegian kroners, and you can see that they're distributed like this: a little bit on the ground and the capture, a lot on transport, and then you also have cross-cutting where it's part of several different of these types of projects mixed together. And with Climate Demo, a few more projects, 62 and 345 million Norwegian climate kroners in financing, and almost the same as R&D, 709 million kroners in total budget. And the distribution is quite the same, but here you also have a small lump to end users. The Climate Program Plan. To look into that, aims of the program are important. They are to develop knowledge, expertise, technology, and solutions contributing to cost reductions and spread of CO2 management, and also utilization of national advantages and development of new technology and service concepts with commercial and international potential. There are, of course, 3 focus areas, and that's decarbonization of industry and energy resources, large-scale CO2 storage sites on the Norwegian continental shelf, and innovative technology development and solutions for CCS. And in addition to this, Climate should also support the realization of gains of Longship. So we always maybe not weigh the projects up towards those gains, but we always look into, and there are different kinds of gains. One of them can, for example, be the expectation of the rise of a market due to the Longship project. Then you have, we also have to look into, or we should prioritize hydrogen production in combination with CCS and have an increased focus on direct air capture and bioenergy combined with CCS, and also a clearer position on social scientific research, which are important for the public perception, for example. Furthermore, projects that receive support should contribute to the attainment of the program goals, and they shall substantiate one or more of the following elements. Cost reductions, that's looking into the CAPEX and or the OPEX of CCS, and then more efficient processes integrating with neighboring systems and economies of scale. Then you have risk reductions. Then we look into both the technical and financial risk reductions involved. Improved efficiency, more efficient CCS technology, for example, through energy efficiency. New technology models, that could be entirely new technology models, or including qualification of new solutions and new methods and or new components. So it doesn't have to be all entirely new. And then, of course, there is an education component. One should educate future experts, including PhD positions and postdoctoral research fellowship. Yeah, the Climate R&D types of projects that they will support. It's described further in the MPE regulations, but the main types are research projects with fundamental research, and research projects should, of course, include a doctoral education. Then you have competence and collaboration projects. They should develop knowledge and build competence that society or the business sector needs to address significant social challenges. And then you have innovation projects in the business sector. And they have to be company-led projects with substantial R&D content. And innovation projects should lead to renewal and sustainable value creation for participating businesses. And this new knowledge should also be made available. Then you have international projects, and here we're back to the ACT and the CETP that I talked about earlier. And here Norway Climate can provide support to Norwegian actors participating in international projects. And for the Climate Demo, we will support projects focusing on development and demonstration of knowledge, competence, and technology for CO2 capture, compression, transport, or other handling of CO2, storage or utilization of CO2 that involves a long-term storage. The types of projects are technical economical feasibility studies, testing of technology at pilot scale, demonstration plants, commercializable service concept or methodologies, professional networking and knowledge dissemination, international projects such as ACT and CETP. So this depends on the TRL because there's an overlap also, but lower TRLs with the R&D and higher with the demo part of Limit. And then benefit realization for the Longship project. And I have no idea how I am on time, but I have 3 slides on the different parts of the chain: capture, transportation, and storage. And for capture, there are several capture technologies already at different levels of maturity. And mature technologies are currently employed in full-scale facilities. But there are expectations that risks and costs can be further reduced over these points here. One should seek to improve, optimize, and reduce risks and costs associated with these mature technologies. Oh, oops, I'm sorry, a little bit trigger happy. One should look into capturing technologies that should be tailored to specific industries and consider factors such as available waste heat, space requirements, electricity consumption, and tolerance for various types of flue gas compositions. There should also be research on breakthrough capture technology and new solutions, including development of sorbents, solvents, membranes, etc. There should be a focus on faster stepwise development towards increasing maturity and substantiating the long-term potential for a capture process. There should also be integrated solutions for industrial processes, simultaneous CO2 capture, hydrogen production with CO2 capture, and air or ocean capture are also areas of interest. And finally, there should be further development and testing of capture technologies ready for scaling up to pilot or demonstration scale, including low temperature capture, solid sorbents, oxy-fuel technologies, and hydrogen combustion. On the transportation, the program can support projects that will help reduce risks and costs for CO2 transport. In addition, the program can support the development of technology and innovation that facilitates the financing and commercial operation of CO2 transport systems. And here relevant areas are how impurities in the CO2 flow affect thermodynamics, characteristics of the CO2 mixture, the corrosive environment, precipitation, and flow conditions in the transport system. For materials, research into and testing of materials throughout the value chain is of importance. And then one also should develop software for simulation of multi-phase CO2 flow. Design of ships and loading, unloading systems, including offshore unloading to liquid intermediate storage or direct injection into storage formations. Whoops. Finally, it's the storage part. Research, development, and demonstration in the following 5 areas are prioritized. You have CO2 wells, where one should look into improving, streamlining, and securing well drilling, safe injections, and subsequent well plugging, and direct injection of CO2 from ships. On the storage reservoir and cap rocks, CO2 injection strategies and water production from reservoirs suitable for CO2 storage are of interest, pressure control, cap rock, and sealing mechanisms. For monitoring, real-time monitoring is of interest, CO2 storage sites and the marine environment both, including, of course, storage operations, shutdown, and post-injection. And here one also have to look at risk and mitigation. For the modeling and digitalization, It's looking into artificial intelligence, automation, to handle capacity, injectivity, sealing, monitoring, and flow properties, and also here as well, risk management. And finally, the social sciences, where you have simplifications and standardizations, looking into hubs where different storage sites can work together or get the CO2 from hubs. And also social science research, looking into legal matters and incentives that can contribute to a market for CO2 storage. And all these three branches of the full-scale CCS, there are already, as you saw, more than 100 projects running, and many of these touch into these areas where I've talked about now. And we're still looking for more projects to support. So there you know about that. There.
Thank you very much, Kerstin. Interesting overview of quite a large body of work over quite a good period of time. This will be a fabulous help for everybody else moving forward. At this point in the program, we've scheduled a short break so that everyone can catch their breath. We'll be coming back at 14:45 or 2:45 European Central Summertime. And we'll be starting on the second half of this session 2. See you all in 5 minutes or so.
Welcome back. It's my honor to present Katrina Lunes Carlsen and Christopher Engenes from the Norwegian Petroleum Directorate. They will present enablers and regulative recommendations for CCS projects. The floor is yours.
So thanks a lot, Adriana. Yep, Christopher Engenes and Katrina Lunes Carlsen. We are geologists in the NPD. And thanks for the invitation. We will give a presentation on the way we work on the regulator side, what enablers and regulative recommendations we have for CCS projects. Norwegian authorities have put a lot of emphasis on identifying suitable CO2 storage locations on the shelf. And so based on subsurface data acquired and experience built by the petroleum industry over the last 50+ years, the NPD has mapped and evaluated the suitable reservoirs for storage across the entire shelf, the Norwegian shelf. So today we will show what the NCS can offer. Significant and safe CO2 storage capacity is already demonstrated by existing projects, and that we now have established a licensing policy and regulative processes for carbon storage. We are indeed seeing a group of companies that are already maturing licenses awarded over the past 3 years. And there is all the time continued interest for more acreage from many companies. So there's been high CCS activities on the NCS for more than 25 years continuously, and new projects are continuously added to the funnel. Multiple projects and strong operational experience is proving that the NCS is indeed suitable for CO2 storage, and combined with the established regulatory framework, Norway is well positioned to continue growing this industry. I would especially like to mention a few of the most important achievements of the past few years. And indeed, you have heard about this a few times already in this workshop, but we would like to repeat some of the most important. So since 1996, Sleipner Field has captured and stored CO2 and is one of the longest lived CO2 projects worldwide. Every year they are storing approximately 1 million tons. It's captured from the natural gas production and re-injected from the Sleipner A platform and into the Utsira Formation up to 1,000 meters below seabed. Valuable experience and expertise has obviously been built for this, which now we can replicate and utilize across the NCS for the CCS industry. The Snøhvit field has since 2008 re-injected CO2. This has been captured from natural gas processing plant onshore at the Melkøya facility up far north in Norway. So the liquid CO2 is then pumped back and returned to the Snøhvit field offshore for re-injection. Technology Center Mongstad, TCM, it's owned by the Norwegian state through Gassnova in partnership with Equinor, Shell and TotalEnergies, is the world's largest and most flexible test center for developing CO2 capture technologies and is a leading competence center for carbon capture. TCM was initially established as the first step in developing a full-scale process to capture CO2. The purpose was to identify, develop, test, and qualify possible capture technologies and technical solutions with the goal of reducing cost, technical, and environmental risks associated with the construction and operation of a full-scale CO2 capture plant. The Norwegian government launched a full-scale CCS project in the Longship/Northern Lights project in 2020. Northern Lights, you have heard about many times, I'm sure, and is responsible for developing and operating CO2 transport and storage open for third parties. That is the biggest difference. It will be the first ever cross-border open source CO2 transport and storage infrastructure and offers companies across Europe the opportunity to store their CO2 safely. Phase 1 of the project will be operational in 2024 according to plan, with a storage capacity up to 1.5 million tons per year. Since 2021, there has been several CO2 storage concession rounds already. And to date, these have now resulted in 5 CO2 exploration licenses and 1 exploitation license. We see continuous high activities from the industry and expect new nominations and additional acreage to be awarded on a regular basis. The sedimentary basins of the NCS are generally well suited for CO2. So this is just a snapshot of the database that we have access to in Norway. This, of course, has built sound knowledge about geological formations such as saline aquifers and reservoirs in depleted reservoirs. All are considered candidates for safe storage. It is key that the reservoir are sealed, obviously, such as the leakage is avoided. We have good control of reservoir seal pairs and other potential leakage mechanisms, of course, such as fault patterns, fracture pressure gradients, and well integrity knowledge across many petroleum licenses are also important to be on top of. And to facilitate for all of this, we have in Norway a well-established and available subsurface database of public data. This is hosted by us in NPD through the Discos database platform. This should obviously be utilized by everybody actively in the evaluation of CO2 storage candidates in the future. So the CO2 license definitions, just to repeat something you may already know, but we have 3 levels of license definitions. One is a survey license. This is the simplest version that gives the right to explore for subsea reservoirs. It does not give an exclusive right to explore in the areas mentioned in the license, and neither does it give preferential rights in the assignment of exploration licenses or license for exploration of a subsea reservoir for storage. That means this is a type of license where you can go out and acquire data, but you will not get access to the area for further exploration and exploitation, which is the next level up. Exploration license gives an exclusive right for exploration in an area with a view towards assessing potential for exploration of a subsea reservoir. It's a bit heavy sentences, I acknowledge that, but this is more a parallel to the standard exploration license that we give for petroleum licenses. And then if it goes to PDO and you decide to develop further into storage, then you need an exploitation license, which gives the right to store CO2 in the area. The first CO2 license, so the first license for CO2 injection and storage was awarded by the MP, as the ministry, back in 2019. This is the exploitation license EL001, which is operated by Northern Lights. This again consists of companies Equinor, TotalEnergies, and Shell. Following the approval of the development plan for the license, we noted an increasing interest for access to CO2 storage, and that started the application purposes or continued it to grow. So for the CO2 storage application process, we have a so-called open door policy. This means that the individual applicants seeking license pursuant at the CO2 storage regulations can apply when there is sufficient technical and a business requirement basis. So it's fundamentally important that you need to have a technical, robust plan and solution, but it has to be backed by a business requirement. That's why this is a kind of an open door on the request basis as of today. So for now, 6 licenses have been awarded. All of them are in the North Sea, except from one that is in the Barents Sea. There is an increasing diversity of industry players now engaging in this business, and so far 10 Norwegian and international players have secured acreage. And in alphabetical order, they are Aker BP, Cape Omega, Equinor, Horisont Energi, OMV, Shell, Stella Maris CCS, TotalEnergies, Vår Energi, and Wintershall Dea. We expect the player picture to be even diversifying further going forward.
Yes, can you just so this shown.
Oh, there is a cartoon.
Yes.
Just put them all.
Okay, so this slide shows the licensing process as of today for both companies and the government. And the companies submits an application which needs to be according to the guidelines, and the MPE and MPD assess if the application is of sufficient quality. If yes, the area can be announced. And for announced areas, normally it has been given a deadline of 6 weeks for submission of application for a license. For both exploration and exploitation permits, final strength and technical competence are essential. And when awarding exploration license, there will be arranged negotiation meetings, and it will be given an obliged work program. And when given an exploration license, the work program normally will include submitting a plan of development or a relinquishment. So CO2 permit application requirements, detailed requirements is found in the guidelines for application of license. And but main takeouts are potential for CO2 storage capacity, risk and probabilities, a description of CCS project, and geological and technological assessment, development plan, monitoring program and license work program, and our environmental assessments. Yes, so NPD has access to all data collected from 50 years of experience from the petroleum industry on the Norwegian continental shelf. And the authorities' access to collected and analyzed data is stipulated in the law. This CO2 Atlas was published in 2014, and it has been prepared to identify safe and effective areas for long-term storage of CO2 on the shelf. The atlases are built on information provided by seismic surveys, plus offshore wells and production data. And during the work on the atlases, the NPD mapped aquifers and other subsurface structures before assessing whether they are suitable for long-term safe storage. And one criterion in these evaluations is that carbon storage should have no operational negative impact on oil and gas operation, either now or in the future. And the storage atlas shows where there is a possibility to store CO2 and how much CO2 it is possible to store. And there is a significant storage capacity in the Norwegian shelf. And an overview of the aquifers on the shelf can be downloaded from our website. NPD have developed large-scale regional models in the Frigg and Heimdal and Troll area in the North Sea. And the aquifer models will be made public. We have discussed cloud and shared with the industry and academia. The models can be easily integrated with operators' internal models with higher resolution. And for CCS purposes, these models can be used for better prediction of CO2 migration and pressure development. So why CCS on the Norwegian continental shelf? We have the knowledge through 50 years of oil and gas industry on the Norwegian continental shelf. We have mapped, collected, and interpreted geodata. We have the experience. CO2 has been injected on the Norwegian shelf for more than 25 years, which we continuously learn from and are monitoring closely. And we have the potential to grow. Our evaluations show there is a potential to store large amounts of CO2 offshore Norway in well-known reservoir models. And we have the regulatory requirements. MPE and NPD have established the regulatory requirements needed to support and follow up the emerging CCS industry. And we are ready. CCS is a key part of meeting our climate targets and decarbonizing the industry, and the knowledge and technology is ready now. So thank you.
So we are actually waiting for our next speaker. Michael is connecting after another commitment. But in the meantime, I found it interesting that you mentioned that all the activities in CO2 should not have any operational negative impact on oil and gas exploration and production. So that shows still the commitment of NPD and the Norwegian authorities to maintain production and keep exploration active for oil and gas. Is that the case?
Yes.
Do you want to elaborate?
Well, these industries are going hand in hand for now. Data from one is all the time enabling the other one. So the strategy from Norway is to, well, that has to be communicated by the leadership of NPD, obviously. But for now, CO2 storage is important for NPD to manage, but it's not how to say it, impacting the petroleum industry as such, other than being a parallel activity.
How do you see the social license to operate in Norway? Do you think that there is enough acceptance from the public for CO2 storage? Because that has been one of the challenges in this industry that is developing, and Norway has the longest experience with this offshore.
Yeah, the acceptance is mostly visible within the economic part. I think that people see how much this costs. I'm not so sure if most people know exactly what they're talking about, like technically. So when we hear about the acceptance in the media, it's more about that the cost of Northern Lights is such and such much a billion, and so it's on the financial side. I think technically, Norway has shown through all projects, Sleipner, Snøhvit, TCM and Northern Lights, that this is something that we can do and manage and make to happen in a safe manner. So there's no kind of public scrutiny as such on technology level as of today. So but of course it has to be rolled out in a big scale, and then I don't know if it will change, but for now there's no problems with it. No.
In terms
it helps
of
it helps that it is far offshore, of course, and it's kind of not, it's not like the more controversial things that you see in your neighbor garden or anything like that. So that makes it easier, of course.
Yeah, it's often, I think even in an article, it's written as not in my backyard. So as long as that is the case, we're happy. In terms of monitoring, while I have you here, how mature do you think are the regulations, given the cost of monitoring CO2 containment? So because the way I see it is we have the technology to do it. I mean, we know that, especially in this industry. However, monitoring for the operators, that means around 20, 25 years, if I remember correctly, with relations in Norway. And that's a liability to operators, but after that, the liability goes to the government. So, and it's very expensive to monitor if we really want all the high-end technology that we use for oil and gas. So I'm just curious if you have any comments about, from your perspective and NPD.
First of all, we have seen the projects we have seen to date have very comprehensive monitoring programs, more in the realm of research rather than commercial production. So it has to be a balance between what is commercially feasible and what is technically a robust solution for any storage project. So I don't think the industry has seen the solution for this quite yet. It will obviously not be an annual seismic survey. The level of repeat has to be good enough to secure that the storage is safe, but at the same time realistic enough to happen throughout the time that the project is living, right? So that balance is something that has to be solved on a project-to-project basis. So I think we know what we need to do, and I'm sure that this will be shaped as we progress, and it will be balanced to the project on a project basis. Exactly how it will look like at the end, I don't think any of us know exactly, but it will be sufficient for each project the way they will be designed at the end, I'm sure.
Thank you. And with that, I would like to thank you, Katrina and Christopher.
Unfortunately, our next speaker is not available, so we're going to take the opportunity to invite all of the speakers who are still in attendance back to the panel for our panel discussion period, and invite any of the participants who wish to pose a question to raise their hand so that they can come forward and ask it verbally themselves.
So 5,000 Northern Lights, Mike, that's a huge number.
Yeah, I mean, it's you know, you have to try and bring this thing into scale, Adrian. And I found at CERAWeek one year I was struggling. So somebody was talking about the IEA paper, and I thought, you know what, I really do need to read that thing properly, because like many in the industry, initially I was a bit cross when this thing came out and just said, yeah, stop it all now, that's the thing to do. And I thought, well, not really, because you're creating trying to solve one problem by creating a whole new set of problems, and that never historically has worked out well. But what I did then go and do and read their proposed, or their calculations on various things that needed to be achieved to deliver the 2050 agreements. And yeah, if you use Northern Lights as a useful sort of unit of measure, 5,000 of them, it's as clear as day. And you heard me then, right? Maybe we'll be somewhere between 700 and 1,000 at the end of the decade, unless there's a massive change in regulatory drivers. And the thing that's at the back of this is there's no consumer engagement. We see all sorts of things around the world, environmental protesters, groups, action groups. But when you go back to the consumer and say things like, will you pay extra at the pump for clean, low carbon gasoline? The answer is no. If we look at the grades of crude out there now, increasingly traders have access to carbon intensity associated with crude. The Norwegian crude is extremely low in carbon intensity, so certain grades of it. Same with Saudi Arabian crude, but on the strike deal, if it's the same price as another batch of crude that's closer to port, the trader will take that, right? Unless there's a win in it financially, they have no interest in trading based on the carbon intensity of crude, even if there's no differential in price. So it's quite interesting where you've got those consumer side apathy to wonder how regulators will move next, right? It's all a bit of a chess game.
Yes.
So on that point, I'm sorry, Adrian, I'll jump in with my quick question since there's no hands up just yet. So Michael, setting that up and assuming nobody wants to take responsibility or pay for those Scope 3 emissions mitigation, what do you think the likelihood of forced regulation is then to address that point?
Well, that's going to be a multi-speed world, isn't it, Anthony? So what will happen there? And I was in an interesting meeting with a group of consultants chatting about that they'd done some work on global regulatory frameworks and yeah, not S&P Global consultants. They used a term that implied that Europe was almost fanatical, at the fanatical end of the regulatory spectrum. Europe's already doing it or trying to do it in some sort of coordinated way, but they wondered whether, you know, literally using the whip all the time is the way to go. But I think that's where we're at, right? So the US has thrown money at the problem to try and stimulate leadership in renewable technology in all the forms. So they've thrown subsidy money and that's made a lot more projects viable than would otherwise have been possible. Latin America, I see very piecemeal interest in anything to do with it. There is interest. You go to Brazil and what have you. And Mexico's talked about it as well, but largely it's on the back burner. Asia wants to do it variably depending on where you are. Africa, of course, is demanding an energy transition that affords equality and affordability and equity, basically. They want a transition of their own making, in fact, an industrial revolution of their own making before they decarbonize. So that leaves Europe and America at the moment and bits of APAC. And so whether or not the world leaders get together for those parts who are at the bleeding edge of it and force it, that's where we seem to be headed. But how do you legislate then when other nations just continue to go full blast with their emissions, and you effectively just become their offset until you sequestrating so much you've no further lever to pull on? It's an interesting debate. I think it will be catalyzed either by some very, very wide global agreement or a complete change in consumer behavior if through the rest of this decade we, for example, see significant and harsh examples of the realities of climate change and weather and things like that, that might catalyze enough of a reaction. But you know, even here in the UK this week, it's very sunny and people are enjoying it. No one says it's the climate change, it's just the weather. So it's very nice.
Thank you, Michael. I think, Stefano, you have posted a question in the chat. Would you like to ask it directly?
Sorry, I lost connection.
No worries, Adriana. I
Okay.
think Stefano's got a question.
Yeah.
Yeah. Okay, good.
Thank you. First of all, Michael, thanks for your summary, which is great in terms of overview. You have been discussing about depleted gas and oil fields. So the question that I have is, maybe the presence of abandoned wells, unmapped wells, is likely to be a major limitation in the storage security in this depleted field. Is that true, or is not a major risk?
So yeah, Stefano, that's a great question. And you know, from a geoscience perspective, saline aquifers aren't the easiest things in the world to deal with. But everybody seems to be much more focused on the potential of saline aquifers. There's an awful lot of projects right now looking at the characteristics of aquifers around the world and their ability to take on carbon dioxide. And it seems to be where most traction is happening, where most of the success stories are. Historically, in EOR settings with CO2 reservoir pressurization, we've seen several fields, not lots and lots of fields, but a significant number of fields that were, perhaps you might say, overpressured, begin to seep through previously plugged and abandoned wells. And that's made people set up and notice. I mean, you have, by the very nature of drilling a well into that reservoir, you've passed through the seal and into the reservoir, and you've created a weakness, which you then hope to solve by plugging and abandoning and sealing. But I think there will be more work done. There will have to be more work done on some reservoirs. We also don't know what the effect of repressurizing that reservoir excessively might be for the seal, right? We've always sort of managed enhanced recovery reasonably well, but in some cases, if you've got a very low margin business, you'll try and squeeze as much as you can in there. And if there's no guidelines on where that thing goes snap, or the seal even begins to fail. So yeah, I think those uncertainties are encouraging people to focus mainly on saline aquifers at the expense of traditional using depleted and exhausted fields. We will continue to see a ramp up, I think, of EOR settings using CO2, because that's a massive environmental win. It helps you with your decarbonisation story for your crude. So,
yes. Sorry, Anders, you have your hand up.
Yeah, I do. I see a little bit more positivism because the price hurdle for the renewable energy sources are behind us. It's cheaper now per kilowatt hour, and of course, an electrification is a massive efficiency gain. Of course, the problem is then, and the molecules are really, really nice because you produce them, you transport them, and you use them when you need them, kind of. So resolving this production consumer gap with alternative solutions, let's say heat storage, molecular storage in the produced molecules, or of course battery storage to some extent, could close most of that gaps. So there is a massive reduction expected in the need for fossil hydrocarbons. And of course, when you include the cost of the societal costs of the externalities upon production, of course, the fossil use are getting less and less profitable for the society, for the individual human being, and of course also this will affect the businesses over time.
But I'd counter that's a very Western view.
Yes, and I know that.
Parts of the world still in heavy industrialization, right? So in Africa,
yeah, but go to Africa and they're not interested in oil and gas. Depends on who you talk to, right? But the point is basically they are not necessarily developing the way in which we did. They could develop to, and there are a lot of examples of that. There are different ways pathways to develop a society. It doesn't necessarily need to follow the Western European one. But sure, we need to maintain good lives for everybody, right? And until now, it has been a massive gain, the oil and the fossil resource, right, for human beings. No question about that, right? The question is what we're going forward, how this will be. Then about this first, second, third of a kind, and of course learning. And so basically, you know, engineering, procurement, and construction scales sublinearly, like with the installed capacity, right? You can, it doesn't take that much engineering work to have twice as big storage or capturing facility, and developing regional scenarios for decarbonization is, of course, as you say, you call it hubs, I call it regional scenarios. I think we mean the same, and it's basically a massive gain there when you break it down to cost per stored CO2. And you also said it, assembly line production, smoothed supply chains, more effective transport, specialized service industry, competition in the market of suppliers and demand, innovation in business models, governmental tools, right? All of these closest reduces the costs going forward.
Yeah, I think
if we want to, right?
what you touch on there is really interesting as well, because in the upstream industry, we've got a very reasonable but evolving ecosystem of partners and innovation. In renewables and in things like carbon sequestration, we're often dealing with people who exist outside upstream and don't understand what we do, how we work, or we expect them to play a part in carbon sequestration. And that whole orchestration of a new ecosystem is I think yet something else that slows things down. We will reach a hurdle point there as well, but we're still some way from it. I see that whole ecosystem is still a bit stop-start in its nature, because people are talking different languages to one another, and they've not developed a way of talking to each other. The language of carbon sequestration has not developed yet, so that's something else that will probably become a lot easier through the rest of this decade.
And then you have your hand up. Sorry.
Yeah, I just wanted to ask Will before. I mean, I know you have your hand up, but Will, just I would like to hear your opinion or your view from the market's perspective of data and exploration in terms of the worldview. So Mike was talking about hubs and actual projects being quite a lot in the North American part of the world, and of course offshore we know there's a lot of activity in Europe. But I know that you have not a different view, a complementary view, and I'm just curious about it.
I mean, one of the interesting things I was just thinking from Mike was around the discussion on hubs. At what point do you have a sort of a point versus a hub? Not just from today. I've heard a lot of talk about it. Well, you know, say for example, you have one project as a hub. Is the North Sea a hub as a large scale basin in which there's lots of opportunities, and it's kind of a scale question on that one, of how you look at those individual regions around the world. There was one thing just on wells as well that I sort of mentioned. You know, the abandoned wells vary dramatically, right? So it's not just about saline aquifers or depleted fields. And I'm repeating conversations I've had, and a common phrase is, yes, it's an abandoned well. It was abandoned to the standards of the day. Those standards can have significant variability, what region you're in, and also what decade you're in. So I think there's a lot of nuances within that coming through to the data thing. Having good, reliable data on what those wells actually are, how they were abandoned, that's an important component of it as well. And in fact, data is I think always a friend.
Well, I think the North Sea is fascinating, right? The way that the North Sea will develop out to 2050 really intrigues me. It's got a lot of ownership in it. Norway, the UK, Denmark, so on and so forth, who are all leaning with different policies, and it's become a sequestration basin that's also hugely wind generative. There's other things being experimented with. There's existing decarbonisation of existing oil and gas production, where potentially the renewable element of power for the asset will exceed the asset's demands and can be re-injected into the grid of the country, providing an offset, if you will, a further offset. So the North Sea for me is a really interesting case study. It's almost, and it's something I did at CERAWeek this year. I got a group of people together, government and policymakers, to talk about whether or not it could be a showcase in the world for an integrated energy basin, if you like. So it's a good example.
Eamon, you've been there a while with your hand up. Would you like to go ahead?
Oh, thank you. I just a comment or a question, because a lot of the activity for CCS is for net zero CCS is in Europe, and maybe traditionally also there's a lot of knowledge and knowledge in the type of monitoring, type of reservoir management, EOR capabilities, but also it's historical, right? So there's a lot of industry in Europe and the United States, predominantly for the coal industry, right? Which predominantly was also producing the carbon 3 years, and that is what we see now as well, is that the population in Asia is increasing, and they require, of course, energy, right? And the easiest is to put in the coal stuff. And of course, we cannot build walls around these different continents. We need to build bridges. And I was wondering, where are we then going, right? So this Norway is a small-scale country, and it's although globally, but has a very advanced technology in that respect. Also, same with UK, and the same with other parts of the country, Europe. So how is it with the transition of experience between different parts of the continents? We had a presentation from Japan yesterday. That was a very interesting one. Do you have any comments on that?
So what did you say, Japan?
Yes, so yesterday we had a presentation from Japan, but for example, if you take India, or the amount of population, the number of populations is increasing, so they require energy. That's the easiest to put coal in place, right? But that's increasing the CO2 emissions.
Yeah. So coal's. Let's be absolutely frank. Coal, and I understand the question now. Sorry, I was struggling just to follow for a moment. Coal is a massive issue. Coal fascinates me. Here's why coal fascinates me. It was under the spotlight. It was under spotlight 2 decades ago for causing acid rain, and it moved further into the spotlight. Just got its head down, and it seems to have been left. There's no Just Stop Coal organization, but there's a Just Stop Oil. And it absolutely fascinates me, because last year, coal hit its highest ever recorded traded volume in the last decade or two. And another fact is that the coal being moved around, on average, is 20% less calorifically valuable than it was a decade ago, and it is a massive issue. I saw what you meant with Japan. Japan authorized 12 coal-fired power stations when they closed down the nuclear set following the disaster at Fukushima, and they did so because they could more readily and easily contract long-term for coal at a known value than they could for gas, which was their preferred option. The gas market, they were really duking it out with China and other nations for LNG cargoes. And they said, you know what, we can do coal, do it as cleanly as possible, but let's do coal. India will go with coal. Africa, interestingly enough, to follow another thread from earlier, would like to not do coal, but use gas. So they will still go gas, but it's cleaner, but it's obviously cleaner than coal, but it's still burning fossil fuel. But yeah, that's what I was trying to say before. We can do what we want in the West, but we are offsetting what others are doing. So whether that thing gets into balance, comes into a favorable state, or actually slips back into an unfavorable state, because say Africa industrializes at a phenomenal rate, its population is massive. Nigeria's population is going to be huge, huge by 2040. Young, demographically young. The West is demographically old. Africa is going to be demographically young. Massive population, massive urbanization. That only goes one way.
Mm-hmm. Will, you had a question?
More of a comment. It was speaking to some of those markets as well, with Southeast Asia in particular being there's a lot of LNG activity, a lot of gas, and a lot of naturally occurring CO2 alongside that gas in that region. And if you look at their export markets, it's where I might be treading a little bit on Michael's proper area of expertise, but their markets are North Asia. That includes Japan, and there's a stated political goal to reduce emissions and the footprint that comes from those regions. Perhaps that's coal with CCS, and we go back some years to that plan. You look at some of the Nigeria, for example, I believe they export to Southern Europe on the gas side. So those sort of political pressures, I think, and the desire for more and more gas exploration in places like Southeast Asia, I think that will play a role in some of the projects that come online perhaps more quickly. They don't necessarily have all of the stakeholders that some of these sort of bigger hub ones do, where there's perhaps less familiarity with those groups of companies doing business together.
Anders, you wanted to contribute a comment?
Yes, I would definitely. I mean, looking at how the global situation is really important, right? It's really bringing things onto the table. But of course, for many people, that it ends up in whataboutism, right? And you feel that you lose the responsibility for your own actions. And I think that we should be very careful about not going into that trap. That does not mean that we should not talk about how they will develop over time and how we can contribute by changing our own attitude and going forward. It's not like they want climate change either, right? So, but of course, we are in a situation where we can do something. They are at a little bit different level, or whatever they is, right? We are talking about the majority of the population. We are just like a small fraction that we're talking about here in the Western Europe. We're like 1,000 in Norway per mil. So we are just nothing, of course, but we have the full responsibility for our own actions. And this goes for individuals, for people, like a region, for the nationality and a whole group of nationalities. So that's just, it needs to be said. I think we should start to talk about the net zero society and the carbon handling and the carbon pricing in carbon handling pricing in net zero society. So there's you can think of a range of different pricing models. You could say that you target a temperature, let's say 1.5 degrees at the end of this decade, and then of course you have a carbon budget, and then you price the carbon accordingly. Like expert sits down and determine what's the global price. You could have a fixed price model like we have here in Norway. It's 69 euro per ton now, and it's going up to 200 in 2030. You could have a quota trading model in the quota sector like we have in EU. You could have a tax reduction scheme like in the US. But what I really like is that if we could make a marginal price model where we laid out the cheapest solutions. Nature does it for free, right? But then there are some of them that are really, really cheap, and it's getting more and more expensive. And then we decide on how much we must capture within, let's say, next year. And that will be determined by the most expensive solution, right? And then, of course, there are large gains for those who can supply capture, transport, and storage at a cheaper price. Then we need to be very careful about where this CO2 comes from, because avoided emissions cannot be used for compensation. But let's say incinerator, trash, burning trash with fossil, that are both fossil and bio, can be used for compensation. I think incinerator will come far earlier than direct air capture, which I don't think is Cloudworks has really something nice going, but capturing from point sources is so much more effective. And when you burn trash, it's like 50-50 fossil plastics, and then of course wood and paper and all of that in the trash. That is basically taking a CO2 molecule from the atmosphere and bringing it down. And we are doing that in Norway now, right? And then we have the voluntary market. So there are lots of possibilities and market innovations coming up now. I need to run because I have kids in the kindergarten that are waiting for me.
Okay, thank you, Anders.
But it has been wonderful to see you all, guys. And I wish you
likewise
all the best the next half an hour or so.
Okay, thank you, Anders.
Thank you.
Ha det bra.
Ha det bra.
Roya, you had your hand up.
Yeah, I have a question about the business model for CO2 capture and storage, and some of it we have already touched upon. And unfortunately, we don't have NPD and Gassnova people on board for the discussion. But still, I would like to discuss it here. That do you think with the incentives and with the tax regime, we can proceed with this larger scale CO2 projects in future, that they become a kind of business, that we can have a business case for these type of activities?
You faded in and out there. I didn't quite hear the second part of your question.
Yeah, I meant that are we able to develop a business case for CCS activities in future in a larger scale with support of with incentives from the governments and with adding tax, with kind of expanded tax regime on the CO2 emissions. With these two things, are we able to push for the CO2 capture and storage to be a kind of business model for industries to operate with that?
That's one of the possible routes that it will unfold by, where it's entirely funded by regulators, but it's through taxation and what have you. But it creates uncertainties for the companies that own the project, because governments change.
Yes.
And governments change, and they can go, no, that's ridiculous. Look at the effect that tax has had on growth, because people are going to a different country because we tax too hard on emitting industries. So I think a country would have to be very consciously selecting, its electorate would need to be very consciously selecting that they wanted a framework that did not attract emitting industries, a clean country. And I think that's what parts of Europe are experimenting with at the moment. But it's a very sketchy place for governments to exist, because they don't know what it means for jobs. And you can gain tax in one place, but then the jobs come down and your income tax revenues go down. So this is the whole problem with funding through regulation and taxation. It's not certain. And I think that's why we see so many projects stalled, particularly in the West, while those who want to fund them keep revisiting the balance book with the calculators, trying to see at what point that project becomes not viable, because if the window's too small, they're just not going to do it. So ideally, and yes, I think for the most part, subsidy runs out. The US cannot print much more money. Subsidy runs out eventually, because subsidy normally means debt, unless you're managing to borrow from a very good source over there to put it over here. Subsidy normally means debt, and eventually your debt becomes too big to service. So you have to do it through regulation, taxation, moving money, but you've got to be so careful about what that does to your economy and how well positioned your electorate, your population is, and on board with your transition story. Because if they're not, as soon as the government changes, the picture changes.
May I ask the next question? Sorry, Adriana. Then do you think CCS is in a position to get independent of these incentives from the government in the next 10 years or by 2030, that it can be as a kind of business for itself?
I'd love you to ask me that question in a year. You know, some businesses are looking at the whole carbon trading system, the way that they get allocated credits, trade them, can use them to pay for sequestration, and that's how some businesses will function, right? They will take payment in the credits, and that's effectively makes the credit a form of currency, and it's something we're looking at very closely. So there is a possibility for that disconnect to happen, but right now, as it's still taking, as an industry, it's still taking its baby steps. I think it's requiring all forms. It's requiring subsidy, regulation, tax, and carbon credits to keep it on its legs.
I just
Thank you very much.
Actually I raised this point to the NPD when they were still here. But one of my concerns in terms of economics of this project is not as much during the lifetime of the project, but after it ends in reality, after you end injection. Because, for example, in California, regulation says that you have to monitor for 100 years after, after you finish injection. I mean, companies do not survive that long. Most companies will not live that long. And then even when that liability doesn't go to the company, after in the EU and in Norway, it's 20-25 years, and sometimes the Norwegian authorities have said that they can take liability after 18 years, the monitoring is still going to continue, and that goes to the taxpayers. So this is not like the commissioning an oil field that is a finite expense. It's a lot of expense, but it's a finite expense.
Well, yeah, I mean, Adriana, you know, go to America today. In fact, go on YouTube and type leaking oil well. There are some horrific videos of beautiful unspoilt forest where people have gone hiking in there, and there's an old pipe sticking out of the ground that's got a mixture of water and oil pushing out of it. It was abandoned in the 1950s. It was capped. The cap has failed and rusted off, and it's leaking. And everyone's arguing over who's responsible for those. There are thousands of them across America, literally tens of thousands of them, leaking quite a lot of pollutants, and everyone's arguing over it. I think what I see when I talk to governments is they're keen to have some sense of ownership, but you're right, it's an arbitrary number. So North America said 99, I've heard 1,000 years, which is plainly ridiculous. What sort of entity and technology is going to monitor for 1,000 years? But it will be probably, as you say, it will be with a company or consortia to manage and indemnify and guarantee that risk for the operating lifespan of the asset and a period thereafter, at which point it will transition to the responsibility of the host government, so wherever the sequestration is, to manage, and that's quite opaque. What a government guarantee looks like, you know, what are they going to do if it starts to leak? Are they going to cut the monitoring to save cost? We all know what governments get up to when they're under pressure. So yeah, it's good. It's really interesting. It's a sketchy thing. We've never had to offer guarantees like that. No one really knows how to do it.
Yeah,
I think TotalEnergies is going to be 100 years old next year.
Yeah, I know that there are companies that survive that long. I mean, we have good examples, but there's not that many. So if you have to monitor for 100 years, I mean, who is going to be that company? Some of them might exist, some of them will not. But besides that, I mean, that's an exaggerated number, of course, but it is true. Well, 99 years, Mike corrected me. Yeah. But still. But the fact, I mean, is you still need to monitor after you change the liability from the operator to the government, or you have the situations that again Mike was referring to, as in abandoned oil and gas from past.
And TotalEnergies, I mean, it's a shame Anders had to go, because of course he mentioned the lowest cost of sequestration as being nature-based. He's not wrong, but there's so much opacity around the reality of nature-based sequestration, and I know Total it's one of those companies where they've had nature-based opportunities for sequestration, offset in Africa, right?
Yes.
But you can't do that, or it's very difficult to do it, because when you're not looking, people run in and cut the trees down to make charcoal to fuel their stoves. And so what you thought was a nice, neat little offset suddenly is suddenly isn't an offset. So, and it's not just Total, everyone's struggled with nature-based. The airlines are being called out for it at the moment.
Yes, they are.
I think Etihad got really told off by Europe and the UK over their Plant a Mangrove Swamp campaign for offsetting flights down to Abu Dhabi, which turns out to be questionable in terms of its science. So.
Yeah, nature-based solutions seems to have a monitoring problem as well, but probably looks like people with guns patrolling to make sure it stays there.
So given that we have the last speaker, I would suggest, Mike and Will, you have one last chance to give your last statement, and then we will close the workshop.
You want me to give a statement?
No, if you want to, I mean, this is your
yes.
last opportunity. If there's something that you're burning to say, you're more than welcome to say it.
No, I mean, Adriana, thanks very much, because when you first approached me and said, can you do this? I was like, oh, goodness me, the SEG is like the brains trust of geophysical engineering in the business. But what's great is to see, as I say, not just here, but at the EAGE, at CERAWeek, what have you, see so many people engaged in trying to solve this, right? Even though we don't even know today how it's going to pay our salaries, but we feel sure that the drivers are there, that what we're doing is not going to be wasted, it's going to be needed. There will come a mechanism for funding it, and it will be a very interesting career opportunity to participate in safeguarding the future of planet and society. So it was great to be invited here today. And you know what also was good? There were questions and discussion. So many times I do a presentation and there's no questions or discussion. So just to see everyone really engaged on this was really fabulous. And again, thank you for the opportunity.
It was a pleasure. And thank you, Will.
Thank you.
Will, any closing statements you wanted to make before we close up?
I just think it's going to be really exciting to see how it all develops. There are plenty of uncertainties there, both on the regulator, the governmental side. I think there are still plenty of uncertainties to go at on the subsurface side as well. And that's an area that needs continuing focus and development of how we do things like monitoring, how we do things like site selection and so on. So I think it's going to be really interesting to watch it evolve.
I mean, we still have work to do here, right? So our skills are still needed, and that's important. Emin?
Yeah, but thank you. It's been a great experience, both the first day yesterday and today. And as you say, Adriana, will have still a lot to do, and then there's a lot of expense and a lot of knowledge into the CCS projects, but a lot of it is coming also from the production oil and gas projects. I think if we do a very good job with these ones, we can transfer good experience into CCS and hopefully make them profitable and then in the future. Any other points before we close? I'd like to say thanks to SEG, to Lori specifically, and
thank you,
Roy and Adriana for organization, helping with the organizing this workshop. But thanks to everyone. Any other statements from anyone?
Thank you. We'll see you next year.
Yeah, thank you.
Bye-bye.
Thank you all. It was a pleasure and very interesting.
Thank you.
Bye-bye.